Hello, fellow Sapiens, and welcome to Sleepless Homo, a quiet corner of the internet where we slow down the noise of the world and let science speak softly. Whether you're here to calm your mind before sleep, to keep company while you work, cook, or just think, take a breath and settle in. This channel is for those who find comfort in curiosity, soft science, not wild speculation, stories told by humble minds that don't have all the answers, but keep searching anyway. If you value this kind of long-form storytelling, please like and subscribe. It helps this calm kind of knowledge reach others who need it. And if you'd like, share in the comments when or where you listen. Before bed, on the road, under headphones, or while shower thinking your way through history. And if you happen to drift off somewhere along the way, I've placed timestamps below, so tomorrow you can pick up right where you left the story, because every chapter is worth it. And as always, stay curious, stay calm. Why do we still talk about a missing link when evolution never actually lost one? The phrase refuses to die. It drifts through documentaries, headlines, even casual conversation, as if somewhere in the depths of history there is a single fossil that could neatly connect them to us. The idea is older than science itself, older even than Darwin. It came from a time when people imagined nature as a ladder rather than a tree, an ordered hierarchy where every creature had its assigned rung, and the human rung just happened to sit on top. To understand why that idea clings to our imagination, we need to visit a world before evolution had a name. In the early 19th century, natural history was a moral pursuit as much as a scientific one. Theologians and philosophers believed the world had been designed according to a perfect plan. In that worldview, everything formed a great chain of being. At the bottom lay minerals, then plants, then animals, and at the summit, humans, halfway between beasts and angels. Each species was a link in this divine chain, and missing links were simply gaps in God's inventory, to be filled by discovery. When fossils of strange extinct animals began turning up in quarries and cliffs, they were seen not as ancestors, but as curiosities, remnants of a past creation wiped away by floods or divine resets. The notion that species could change into one another was not only unthinkable, but offensive to a natural order designed from the start. Yet cracks began to appear in that certainty. Throughout the 18th and 19th centuries, geologists realized that Earth was far older than the few thousand years allowed by biblical chronology. Layers of rock told a story of vast, unimaginable time, and within those layers were forms of life that seemed to appear and vanish in succession, hinting at change through ages rather than instant creation. But change toward what? Early thinkers such as Jean-Baptiste Lamarck imagined life striving upward through inherent improvement, like a cosmic staircase where creatures climb toward perfection. It was a comforting vision. Progress, direction, and purpose. And when Charles Darwin finally proposed natural selection in the middle of the 19th century, his theory was often misread through that same lens of progress. Darwin never said evolution had a goal. He described it as adaptation to circumstance, endless, branching, sometimes directionless. But the public, eager for a simple story, saw it as ascent. They wanted a clean before and after, ape then human. The missing link idea was born from that hunger for narrative clarity. If humans came from other animals, there must have been a halfway creature, part beast, part person, waiting to be discovered. The fossil that would solve the discomfort of being related to everything else. By the late Victorian era, that craving for a link between ape and human had merged with empire, religion and spectacle. Museums filled with bones arranged as moral lessons, progress from the primitive toward the civilized. Illustrators gave it shape. In the early 20th century, one drawing would come to define the myth completely. A simple line of silhouettes marching from a crouched ape to an upright man. It appeared in a Time Life book on evolution in the 1960s, but echoed images from decades earlier. Scientists never used it as evidence, yet it colonized the public mind. You can see it still on t-shirts, logos, and memes, as if our story could be summarized by a straight line of better and better versions of ourselves. The March of Progress is one of the most successful scientific misunderstandings ever printed. What that image hides is the actual shape of life, tangled, branching, full of dead ends and returns. Evolution is not a ladder. It is a tree whose limbs sometimes reconnect and whose leaves are never final. Every species alive today, from yeast to humans, is equally evolved, equally ancient in descent. The phrase missing link survives because our brains like tidy stories more than tangled ones. We want a bridge between categories, a single fossil that can settle all the questions about where we came from. But nature rarely gives us bridges. It gives us floods, deltas and meanders that change their course faster than we can map them. Scientists have tried for over a century to retire the phrase. In paleontology, the term now sounds almost folkloric, like dragon or philosopher's stone. Yet journalists revive it every few years whenever a new hominin's skull is found. The missing link discovered makes a better headline than new data adds complexity to an already intricate model of hominin divergence. Part of the blame lies with the way early science communicated itself, by analogy, by spectacle, by reassuring readers that humans were still special even within evolution. Every discovery was framed as another step toward modern humanity, never as evidence of diversity or coexistence. The persistence of the myth also says something about us. We find comfort in linearity because we experience time that way. We are born, grow, age, and die. So it feels natural to imagine that species do the same. But evolution does not grow old. It proliferates. It is a conversation between genes and environments, not a journey toward enlightenment. Calling one fossil a link implies that something was missing, when in truth the only thing missing was our understanding. Each species that ever lived was complete in itself, perfectly adapted to its own moment, not an unfinished version of something better. In modern biology, the word transitional form replaced missing link. It describes fossils that show traits bridging major groups, like fish with wrist bones or reptiles with feathers. These are not halfway creatures, they are mosaics, reminders that change happens gradually and unevenly. Every generation is transitional because evolution never stops. The phrase missing link suggests there is an endpoint, a final perfection. The fossil record shows the opposite, continuity without finality. Still, the myth endures because it scratches a deeper itch, the desire to see ourselves as different. Even when we accept evolution, we want to know the moment it produced us, the point when intelligence, morality, or consciousness appeared. But those too are not single events, they are gradients. Our ancestors did not wake up one morning self-aware. Awareness accumulated slowly, built from cooperation, memory, and shared survival. The search for a missing link between animal and human is really the search for the moment we started asking why. And that moment, inconveniently, has no fossil. There is another reason the term lingers. It flatters the storyteller. To find the missing link sounds heroic. A single discovery that explains everything. Science, however, advances not by final answers, but by accumulating evidence and then admitting what remains uncertain. In that sense, humility is the real missing link in our narratives. The closer we look, the less linear things become. Fossils overlap in time. Traits evolve, vanish and reappear. Even our own species is not a clean continuation, but a collage of ancient genes, woven from populations that mixed and remixed across continents. If evolution is a story, it is not a novel with a beginning and end, but an anthology written by countless authors, most of them long extinct. The word link is too simple for that kind of complexity. Yet its persistence reminds us of how language shapes thought. We name things to understand them, but words fossilize too, and sometimes the old ones refuse to fade. Missing link survives as linguistic sediment, a relic of when we imagined nature built for our benefit, when discovery meant dominion rather than curiosity. Science today sees the world differently. The more we learn, the more the boundaries blur. Humans are not the summit, but one recent branch on a tree that keeps growing. Chimps are not our past. They are our cousins, still evolving alongside us. Every species that has ever lived was, in its moment, exactly as modern as we are now. That realization does not diminish humanity. It situates us within something larger, a 4 billion year conversation between life and environment. The myth of the missing link is comforting because it promises closure. The reality of evolution is humbling because it never ends. So why do we still speak of a missing link? Maybe because the link we are missing is psychological, a connection between evidence and acceptance. We know evolution happens, yet we still crave a picture simple enough to fit on a poster. But truth is rarely poster-shaped. It is layered, messy, and sometimes contradictory. The more completely we accept that, the closer we come to seeing ourselves honestly, not as the goal of evolution, but as one of its temporary experiments. And perhaps that is the real reason this idea refuses to die. It satisfies both our ego and our anxiety, the comfort of being special and the fear of not being special enough. Science cannot cure either feeling, but it can give us perspective. We are not missing links between ape and angel. We're ongoing links between past and future. Every child born today carries 4 billion years of unbroken lineage, a chain not of perfection, but of persistence. That chain was never missing, only misunderstood. We may never erase the phrase from popular speech, but we can change what it means. Instead of a single fossil, the missing link can stand for curiosity itself, the bridge between ignorance and wonder. The next time you hear it, imagine not a half-human crouched in the dust, but the endless process of discovery, still unfolding, still incomplete, and beautifully so. As far as we know, that is the closest thing to truth we have found so far. What if the battle over one tiny fold in the brain decided how we see ourselves? It sounds absurd that the shape of a ridge deep within the skull could ignite one of the fiercest scientific quarrels of the 19th century, but that is exactly what happened. The argument would define how Victorian England thought about the boundary between human and animal, and it would expose how science and belief, anatomy and ego can become inseparable. It all began with an idea, a man, and a piece of brain that refused to behave politely. By the middle of the 1850s, the great debate over human origins was already smouldering beneath the surface of polite society. Charles Darwin had returned from his voyage aboard the HMS Beagle more than a decade earlier, quietly assembling the evidence that would lead him to the theory of evolution by natural selection. He waited 20 years before publishing, fully aware that the idea would be a cultural earthquake. In that pause, other men filled the vacuum, men who shaped natural history into something like theology dressed as science. One of them was Richard Owen, a brilliant anatomist, fiercely intelligent, but equally fierce in his conviction that humanity stood apart from the rest of life. Owen was the kind of Victorian who believed that the natural world reflected divine order, that every species had been crafted according to purpose. His lectures were elegant sermons on design. His museum displays were moral lessons in bone, and to him, evolution, at least the kind proposed by Darwin, was not only bad science, but bad manners. When Darwin's On the Origin of Species appeared in the year 1859, the public found itself suspended between fascination and dread. Here was a theory suggesting that life, all life, from beetles to bishops, had arisen through a blind, indifferent process. Adaptation to circumstance, trial and error, played out across unfathomable time. No guiding hand, no hierarchy, no perfection, just persistence. For those raised on the idea of divine creation, the implication that humans shared ancestry with apes was a kind of philosophical scandal. Yet others found liberation in the thought, a world governed by natural law, not decree. Among them was Thomas Henry Huxley, a biologist of restless energy and razor intellect, who saw in Darwin's theory not heresy but elegance. Huxley became Darwin's unofficial defender, Darwin's bulldog, as the newspapers liked to call him. The battlefield between Owen and Huxley was not a courtroom or a pulpit, but the Royal Institution lecture halls of London. Here, beneath chandeliers and brass railings, the debates of science unfolded like theatre. The weapon in this particular duel was the brain. Owen had declared with great authority that human brains contained a structure absent in all apes, a feature called the hippocampus minor, a small fold deep within the posterior horn of the lateral ventricle. He insisted it was a unique mark of humanity, the anatomical seat of reason and moral capacity. For Owen, it was evidence that humans were not just clever animals, but a separate creation entirely. The hippocampus minor became, quite literally, the line between man and beast. Huxley, infuriated by what he saw as both arrogance and error, resolved to test the claim. In the spirit of Victorian empiricism, he did so by the most direct method possible: dissection. Over long nights in anatomy labs, Huxley obtained and examined the brains of monkeys, gibbons and chimpanzees, sometimes with students, sometimes alone, the smell of formaldehyde filling the room. What he found was simple and devastating. The hippocampus minor was present in apes after all. The difference Owen had proclaimed was an illusion, a matter of scale, not of kind. In the folds of grey matter, Huxley saw continuity, not separation. And that, for him, was the point. Humans were a variation within nature, not a divine exception to it. When Huxley presented his findings to the British Association for the Advancement of Science in the early 1860s, the room reportedly buzzed with tension. To many in the audience, this was not merely a dispute about a ridge in a brain. It was a question of human dignity. If Owen was wrong, then the line between man and ape had blurred. In the polite circles of London, such a thought bordered on indecency. Newspapers framed it as a moral battle, caricaturists drew apes in academic robes, and sermons denounced the creeping influence of Darwinism. But in the quiet realm of data, Huxley's dissection stood firm. Anatomically, the hippocampus minor was there, measurable, repeatable, undeniable. The argument, however, refused to die quickly. Owen doubled down, insisting that even if the structure existed, its proportion or placement still distinguished the human brain as unique. He published intricate diagrams, wrote papers, and lectured to crowded halls defending his position. But each defence sounded more like theology wrapped in Latin. Huxley, with his characteristic wit, answered in public lectures designed to educate not only colleagues but citizens. He used lantern slides to show comparative skulls, turning dry anatomy into living illustration. In doing so, he reshaped science communication itself, making it something the public could witness and judge. Behind the rhetoric lay a deeper discomfort. If humans were not defined by anatomy alone, what did define us? Intelligence? Language? Morality? Huxley was cautious not to claim that humans and apes were identical. He knew that differences existed: brain size, structure, behaviour. But he also knew that difference did not require divine exemption. The truth, he said, is that man differs from the higher apes, not in kind, but in degree. It was a small sentence that carried a revolution inside it. Darwin watched much of this unfold from a distance. His health was poor, and he rarely entered the fray directly. Yet he recognised the symbolic importance of Huxley's campaign. In letters, Darwin expressed both gratitude and relief. "Oh Lord, what a thorn you must be in the poor dear man's side," he wrote of Owen. The hippocampus debate had become a microcosm of evolution itself. Old certainties confronted by evidence that refused to fit their design. For Victorian society, the implications were profound. If the human brain was not categorically different, then perhaps the soul was not either. The hierarchy of nature, that comforting ladder from invertebrates to angels, began to wobble. Some found this terrifying, others found it exhilarating. The press treated it like sport. One magazine mocked Owen with a cartoon showing him chased by apes wielding dissecting knives. Another praised Huxley for proving that even the meanest monkey had a mind. The debate had escaped the laboratory and entered the drawing rooms of the empire. It might seem quaint today, this quarrel over a wrinkle in the brain, but it was one of the earliest examples of how scientific evidence could challenge deeply held worldviews. It showed that data, however small, could threaten identity, and it revealed how easily intellect can be swayed by belief. Owen was not a villain. He was a man shaped by his time, by a world that equated hierarchy with meaning. To admit continuity between human and ape would have been to unravel that world. Huxley, for all his sharpness, was also a product of his era, confident in progress, convinced that reason would prevail over superstition. History, as usual, proved both right in some ways and blind in others. In retrospect, the hippocampus debate did more than settle an anatomical question. It marked a turning point in how science defined humanity. Before it, man was a category apart. After it, human became a position within a continuum. Still special, perhaps, but not separate. That shift rippled outward through anthropology, psychology and philosophy. It opened space for questions that scientists are still trying to answer. What makes consciousness possible? Is morality a product of evolution or invention? And why do we still feel the need to draw lines between us and them? Looking back now, one cannot help but smile at the irony. The hippocampus minor, once the supposed signature of divine distinction, is today just another fold among many, of interest mainly to neuroanatomists. Its controversy has faded into footnote. Yet the echoes remain whenever someone insists that humans are more evolved, or that intelligence proves destiny. The 19th century argument over a tiny piece of tissue reminds us how stubbornly we guard the idea of being exceptional. Science has since peeled away many layers of that pride, but the impulse survives in subtler forms, in our technologies, our hierarchies, even our metaphors. We still speak of higher and lower species, as if evolution were a staircase instead of an intricate web. The truth, as far as we know, is both less flattering and more beautiful. The same principles that shaped the hippocampus in an ape shaped it in us. The same chemistry that made an early fish twitch toward land now lets us write symphonies. There is no clean break, only continuity adorned with complexity. In the end, the story of Owen and Huxley is less about who was right than about how science learns. Knowledge advances through correction, through debate, through the slow erosion of certainty. The hippocampus minor was never the true prize, humility was. To realize that humans are not an exception but a participant in nature is not to lose meaning but to gain perspective. So perhaps that single fold in the brain did decide how we see ourselves, though not in the way Owen imagined. It taught us that the boundaries between human and animal, reason and instinct, are less like walls and more like gradients. We are still mapping those gradients today, still trying to understand what consciousness truly is, and still occasionally mistaking pride for proof. The hippocampus minor, small as it is, continues to whisper a lesson across centuries, that truth, when finally seen clearly, is rarely what we hoped, but always what we needed. As far as we can tell, that is what the evidence shows so far. When science went treasure hunting, what were they really looking for? In the last decades of the 19th century, a strange fever gripped the learned men of Europe. It was not the lust for gold or empire, though those desires ran beneath the surface like familiar currents. It was the hunger to find the creature that would stand between humanity and the animal world, the long-imagined bridge, the Ape-Man. The great museums of London, Paris and Berlin turned into staging grounds for expeditions. Scholars, missionaries, soldiers and adventurers fanned out across the colonies with crates, notebooks and hammers. Every fossil they pried from the soil promised a glimpse of the story that no one yet knew how to tell, how intelligence had evolved from instinct. The search began as a competition of pride as much as of science. After Darwin's theory shook the foundations of creation, Europe's naturalists wanted proof that evolution had a shape, a face, and preferably a human one. The idea that humans were descended from apes was unsettling. To make peace with it, many believed they needed a single specimen to represent the moment of transformation, a missing body to fill a missing narrative. Evolution might be a tree, but what they wanted was a rung. It was a mistake born of metaphor, but a powerful one. The newspapers called it the hunt for the missing link, and soon it was being discussed in drawing rooms, parliaments and pulpits alike. The centres of empire provided the funding. Colonial expansion offered the field sites. Africa and Asia were imagined as living museums, continents where the ancient and the primitive still lingered in both animals and people. This assumption was not just wrong, but deeply political. It allowed European scientists to cast themselves as explorers of the past, even while studying the present. The jungle and the desert became time machines. In those imagined landscapes, the line between anthropology and adventure blurred. Fossils were trophies, and knowledge itself became a form of conquest. Into this atmosphere stepped a young Dutch anatomist named Eugène Dubois. He was restless, brilliant, and dissatisfied with the safety of European laboratories. Born in the 1850s in the Netherlands, he trained as a physician and anatomist, but his imagination was captured by the debate stirred by Darwin. If humans had truly evolved from ape-like ancestors, where had that transformation occurred? Darwin had suggested Africa, based on the kinship between humans and African apes. But the intellectual tide of Europe still drifted eastward. Asia, with its ancient civilizations and its distance from colonial guilt, seemed a more palatable cradle for humanity. Dubois, ambitious and stubborn, decided he would find the proof himself. He left Europe in the late 1880s, joining the Dutch colonial army in the East Indies as a military doctor, a respectable disguise for his deeper mission. He told his superiors that his interest was in tropical diseases. Privately, he was chasing ghosts. The islands of Sumatra and Java were dotted with limestone caves and riverbanks, rich in fossils of extinct animals, elephants, rhinoceroses, and giant tigers. Somewhere among them, he believed, would lie the remains of a creature that walked upright but still bore the mark of its ape-like past. The work was brutal. The heat was relentless and the mosquitoes merciless. Dubois spent years scouring river terraces, aided by local labourers who barely understood what he sought. They were told to bring him bones. Any bones that looked unusual. Crates of fossils were shipped to his camp, then sorted by lamplight into piles of animal fragments. For long stretches he found nothing of interest, yet he persisted with the kind of single-minded devotion that borders on obsession. "I will find the missing link," he wrote in his notebook, as if sheer conviction could bend geology to his will. In the year 1891, on the banks of the Solo River, near a small Javanese village called Trinil, one of his workers uncovered a fragment of a skull cap. It was thick, heavy, and strange, too small to be human, too large to be that of an ape. Nearby they found a thigh bone that seemed distinctly adapted for upright walking. Dubois could hardly contain his excitement. Over the following months, more fragments emerged, teeth, bits of jaw, and additional bone. He assembled them on his table like pieces of a sacred puzzle. To him, the message was clear. This was the creature he had imagined, the transitional form that Darwin's theory demanded. He named it Pithecanthropus erectus, the upright ape-man. The term was not entirely his invention. It came from an earlier German evolutionary thinker, Ernst Haeckel, who had coined Pithecanthropus alalus, the speechless ape-man, as a hypothetical ancestor of humans. But Dubois believed he had found the real thing. The fossils, he argued, belonged to a being that walked on two legs like a human, but had a brain smaller than half the size of ours, a perfect bridge. When he returned to Europe, Dubois expected applause. Instead, he met disbelief and ridicule. His peers accused him of forcing together bones from different species. Some dismissed the fossils as belonging to an extinct giant gibbon. Others mocked his self-promotion. Yet Dubois refused to back down. He carried plaster casts of his discovery from city to city, lecturing in a tone that mixed scientific zeal with missionary fire. Audiences packed the halls, not necessarily to learn, but to witness the man who claimed to have found humanity's shadow. The controversy revealed the deeper problem with the missing link obsession. Everyone agreed evolution must have left traces, but no one agreed what those traces should look like. Did the ancestor of humans have a large brain first and an upright posture later? Or did walking come before thinking? Dubois' fossil seemed to suggest the latter, but that contradicted the Victorian conviction that intelligence was the first and defining leap. The idea that an almost human creature might have walked the earth with a small brain offended the hierarchy of mind that underpinned European self-image. In truth, Dubois's find was remarkable. We now recognise it as one of the earliest known examples of Homo erectus, a species that thrived for nearly 2 million years across Africa and Eurasia. But at the time, the discovery was an orphan. Without the tools of radiometric dating or a broader fossil record, scientists could not place it precisely in time. Some saw it as too ape-like to be human, others too human to be an ape. It became a mirror reflecting each scientist's biases. Meanwhile, the race to find more ape-men intensified. Expeditions funded by European universities and wealthy patrons spread through India, China, and Southeast Asia. Fossils of ancient animals, elephants, rhinoceroses, mastodons, were shipped back to museums in crates stamped with colonial insignia. The few human bones that turned up were treated as relics rather than evidence. Anthropology was becoming global, but its methods still bore the fingerprints of empire. Even as Dubois defended his discovery, other scientists were chasing different versions of the same dream. Some searched the limestone caves of Europe for traces of primitive humans. Others looked to the dry valleys of Asia, convinced that aridity preserved the past. fossils were sometimes misidentified, mixed with animal bones, or altered by eager collectors. The lack of context made it easy to weave grand theories from small fragments. The Ape-Man became less a person than a projection, a myth wearing the mask of science. Behind the professional rivalries and the flawed assumptions, something important was happening. For the first time, the study of human origins was leaving the armchair and entering the field. Geology, paleontology, and anthropology began to merge into a single endeavour. Field notes replaced speculation, stratigraphy replaced storytelling. The same tools that imperial powers used to map their colonies were now mapping time itself. There was still arrogance in the method, but also progress. Knowledge was beginning to be wrested from the ground, not conjured from imagination. Eugène Dubois never quite recovered from his disappointment. He withdrew from the public eye, storing his precious fossils under his own bed for years, rather than surrendering them to skeptical institutions. Yet his discovery planted a seed. By the dawn of the 20th century, new fossils would begin to surface across Asia, gradually confirming that his strange Ape-Man had indeed existed, and that the human story was older and more widespread than Europe had ever dreamed. The search for the Ape-Man was not just a quest for bones, it was a reflection of a deeper need to define what being human meant. In the late 19th century, science was learning to replace myth with measurement, yet it often carried old myths forward under new names. The missing link was less about biology than about belonging, a way to draw a line between us and them, between civilized and primitive, between Europe and the rest of the world. By looking for a single transitional species, scientists hoped to find not just our past, but our purpose. Today, the fossils that Dubois found are carefully stored in museums, their significance re-examined through modern eyes. They remind us that truth often arrives wrapped in imperfection, and that even misguided searches can lead to discovery. The Ape-Man that Dubois imagined never existed as he pictured it, but the bones he uncovered became the foundation for understanding our shared ancestry. In hindsight, we can see that science in the Age of Empire was never just about facts. It was about who had the authority to interpret them. The landscapes where fossils were found were already inhabited, their histories already deep. Local workers who unearthed the bones rarely received credit, their labour folded into the larger narrative of European achievement. The missing link was always framed as something Europe would find, not something the world already contained. That bias shaped the entire field for decades to come, and yet, out of that flawed beginning came something valuable, the realization that the story of humanity was global. That discovery would eventually force scientists to rethink not only where we came from, but how we search. The treasure hunt would give way to collaboration, and the idea of a single Ape-Man would dissolve into a more intricate and honest portrait of evolution, a tapestry woven from many species, not one. Perhaps that was what they were really looking for all along, though they could not yet see it. Not the bones themselves, but the meaning of continuity. To understand that the link between ape and human was not a single creature waiting in the dirt, but the slow unfolding of change across millions of years. A truth more complex, more humbling, and far more interesting than any one fossil could ever be. As far as we can tell, that is what the evidence shows so far. How did a forged jawbone rewrite textbooks for 40 years? It began, as so many great deceptions do, with the hope of finding something too perfect to be true. The year was 1912, and Britain was still an empire certain of its place at the top of the world. The idea that humans had evolved from ape-like ancestors was by then widely known, but the evidence felt incomplete, the fossil trail uneven and frustratingly foreign. France had its Neanderthals, Germany its prehistories, and even the far-off Dutch East Indies had yielded Dubois' Ape-Man. Britain, the self-proclaimed heart of civilization, had nothing. And so, when an amateur archaeologist named Charles Dawson claimed to have discovered ancient human remains in the Sussex countryside, the scientific world was ready to believe him. Dawson was a curious figure, a solicitor by profession, but one of those restless Victorian gentlemen for whom science was a pastime, part adventure, part social currency. He had already dabbled in geology and paleontology, sending bits of Roman tiles and prehistoric tools to museums. What he craved was recognition. the kind of discovery that would etch his name alongside Darwin's in the chronicles of natural history. In a gravel pit near the quiet village of Piltdown, he believed he had found it. The story he told was simple. Local workers had uncovered fragments of a skull while digging for road material, and he had retrieved them for study. The bones, he said, looked unusually thick and ancient. When Dawson presented his find to Arthur Smith Woodward, Keeper of Geology at the British Museum, the professional scientist immediately saw potential. The skull fragments were human, but oddly primitive. Soon, Dawson and Woodward returned to Piltdown to excavate further. Within weeks they uncovered more pieces, a jawbone, teeth, and tools made of flint and bone. The jaw seemed ape-like, but the molars showed human-style wear. The skull's cranial capacity was large, nearly that of modern humans. Together, they seemed to form a creature perfectly poised between ape and man. To a nation still grappling with its place in evolution's messy story, the fossil offered a flattering compromise, an ancestor that looked both ancient and unmistakably British. At a meeting of the Geological Society in December of 1912, Woodward announced the discovery to a packed room. The new species, he declared, was 𝐓𝐈𝐌𝐿 dawsoni, Dawson's Dawn Man. The press was ecstatic. Headlines proclaimed the missing link found in Sussex. Artists painted reconstructions of a noble, browed figure, more philosopher than brute, gazing out over the mists of prehistory. Scientists marvelled at how conveniently the Piltdown skull fit their expectations. A large brain case, as reason would surely evolve first, combined with a primitive jaw, showing that intellect preceded adaptation. It confirmed what many already wanted to believe, that human evolution was not centred in distant savage lands, but right here in the green fields of England. For years, the Piltdown fossils were treated with reverence. They were displayed in glass cases at the British Museum, studied by scholars and printed in textbooks. The discovery seemed to tie the whole human story together. But from the beginning, a few details refused to sit comfortably. The jaw did not fit neatly with the skull fragments. The canine tooth found separately seemed suspiciously convenient. The bones were oddly stained, their surfaces treated in a way that made them appear ancient. Yet each doubt was silenced by the authority of the finders and the weight of national pride. It was easier to accept a miracle than to confront the possibility of deceit. Across Europe, the Piltdown model influenced how scientists imagined human evolution. It suggested that the first step toward humanity was the expansion of the brain, a very Victorian idea, one that placed intellect and reason above all else. When fossils from Asia, such as Dubois' Pithecanthropus erectus, appeared with small skulls but human-like jaws, they were dismissed as side branches, not ancestors. The Piltdown Man became the standard by which all other finds were measured, even as its proportions made less and less sense. Decade after decade, the Piltdown fossils maintained their hold on science. They appeared in diagrams linking apes to humans, and their silhouette crept into museum murals and schoolbooks. Few dared to challenge them directly. Some tried, but criticism was brushed aside as heresy or envy. The authority of British science, coupled with the need to believe that civilization's roots lay close to home, made Piltdown nearly untouchable. Behind the scenes, Charles Dawson basked in his fame. He corresponded with leading scientists, was elected to societies, and hinted that even greater discoveries lay ahead. But in 1916 he died suddenly, leaving his motives and his secrets sealed forever. After his death, new fossils began to appear elsewhere, each contradicting the Piltdown model in some way. Finds in Asia and Africa pointed to a smaller-brained but upright ancestor, not the big-brained gentleman of Sussex. Yet the myth persisted. The bones themselves sat quietly in the museum, their authenticity seldom questioned, their story too deeply woven into national pride to unravel. It was not until the middle of the 20th century that skepticism returned with force. The methods of science had evolved. Chemistry, microscopy, and fluorine dating offered new tools for testing fossils. When researchers applied these to the Piltdown remains in the late 1940s and early 50s, the results were astonishing. The bones were not hundreds of thousands of years old as Dawson had claimed, but only a few centuries. The jaw belonged not to an ancient ancestor, but to an orangutan. The teeth had been filed down to mimic human wear, and the entire assemblage had been artificially stained to appear ancient. The Great Dawn Man of England was a forgery. The revelation spread through the scientific community like wildfire. Textbooks were rewritten, displays quietly dismantled. The shock was not only that the fossils were fake, but that so many brilliant minds had accepted them for so long. The hoax had endured precisely because it told people what they wanted to hear. The discovery flattered human exceptionalism, reinforced national pride, and aligned neatly with a Eurocentric vision of evolution. It was a story too elegant to question. Even now, the full truth of who orchestrated the forgery remains uncertain. Most evidence points toward Dawson himself, a man with a history of dubious artifacts and a pattern of embellishment. Some believe he acted alone, others that he may have been assisted by associates from the museum. Whoever was responsible, the skill was undeniable. The orangutan jaw had been treated with chemicals, the bones stained with iron solution and chromic acid, and even the gravel around the site subtly manipulated. It was deception not born of clumsiness, but of precision. The Piltdown hoax left deep scars on the scientific world. For 4 decades, it misled research, distorted theories, and delayed the acceptance of genuine discoveries that contradicted it. More importantly, it revealed a vulnerability that still haunts science: the ease with which cultural bias can masquerade as evidence. The hoax worked because it fit the expectations of its time, because scientists, like everyone else, are human, drawn to stories that confirm what they already believe. In hindsight, the Piltdown episode feels almost theatrical, an object lesson in humility. It shows how even the most rigorous discipline can be seduced by vanity, and how truth can be hidden in plain sight when pride blinds the eye. Yet it also reminds us that science, though fallible, is self-correcting. It may take decades, but eventually evidence wins. This same skepticism that exposed the forgery also fortified the field. The next generation of paleoanthropologists would approach fossils with greater rigour, demanding context, reproducibility, and independent verification. Standing today before the Piltdown bones preserved in their museum drawer, one can almost admire their craftsmanship, not for what they proved, but for how thoroughly they tested the integrity of a discipline. The stains still cling to the surface, an artificial patina over a very human story of ambition and belief. In the end, 𝐓𝐈𝐌𝐿𝐼 dawsoni never existed, but its ghost lingers as a reminder that discovery is not just about finding, but about seeing clearly. How many truths have we buried under the comfort of what we wish were real? The lesson of Piltdown is not that science failed, but that scientists are part of the same fragile species they study, capable of insight and error in equal measure. The missing link they sought was never in the Sussex gravel. It was in the gap between evidence and expectation, between curiosity and certainty. And in that sense, the real Piltdown man was not the bones, but the mirror they held up to us all. As far as we can tell, that is what the evidence shows so far. Could a small skull from South Africa undo half a century of arrogance? When the fossil arrived at Raymond Dart's house in late 1924, it came wrapped in newspaper, its edges still caked with limestone dust. Dart, an anatomist at the University of the Witwatersrand in Johannesburg, had been teaching students about the human nervous system when a friend, the quarry manager at Town, mentioned strange bones found in a block of rock destined for the university's geology collection. At first, Dart wasn't expecting much. South Africa was not yet considered a serious hunting ground for early humans. The great fossil discoveries, people believed, were made in Europe and Asia, where Piltdown Man and Java Man had already written the supposed script of our evolution. Africa was seen as a stage for wild animals, not ancient ancestors. But when Dart began to chip away the limestone with the careful patience of a surgeon, something began to stare back. From within that hard matrix, the face of a child slowly emerged. Dart was struck first by its delicacy, the small jaw, the round orbits, the subtle curve of a forehead. Yet it was unlike any human child he had seen. The teeth, especially the canines, looked ape-like, and the brain case was small, far smaller than the human skulls in his lab. But the position of the opening where the spine entered the skull, the foramen magnum, was placed beneath rather than behind it. That suggested the creature had held its head upright on its body, walking on 2 legs rather than 4. A small brain, yes, but a biped nonetheless. To Dart, that combination meant only one thing. This was an ancestor, one that walked before it thought. He called it Australopithecus africanus, the southern ape of Africa. The fossil, he wrote in 1925, is not a man, but it is more nearly related to man than any other known form. The scientific community's reaction was swift and cold. British scholars, still under the spell of the Piltdown model, were appalled. How could humanity's origins lie in Africa, and worse, in something with such a small brain? At the time, the intellectual tradition of the European anthropology placed the brain at the centre of evolution. Intelligence, reason, and self-awareness were seen as the crowning achievements of creation. For Dart to suggest that upright walking, a physical adaptation, not a mental one, came first, was not merely controversial, it was heretical. In the polite but unforgiving language of academic journals, Dart was ridiculed. His fossil was dismissed as a young chimpanzee, or perhaps an odd mixture of species. The influential anatomist Sir Arthur Keith wrote that the specimen might represent nothing more than an anthropoid ape of some unusual type. Other scholars argued that the foramen magnum's position had been misinterpreted, that the supposed signs of bipedality were illusions. The British Museum, guardian of the Piltdown remains, showed no interest in examining it further. Dart's idea that the cradle of humanity might rest in southern Africa was simply too uncomfortable, too radical, too contrary to the comfortable narrative that had kept Europe at the evolutionary centre. But Dart was convinced the little skull told the truth. He spent months meticulously preparing the fossil, removing layer after layer of stone to reveal the brain's impression left inside the cranium. That internal cast, an endocast, showed details of the brain's surface. It was larger than an ape's of similar size, with hints of the expansion that would one day characterise Homo. The frontal lobes, though still primitive, showed traces of reorganisation. The teeth, too, spoke of change. The child's molars were human-like, and its jaw lacked the projecting muzzle of apes. Each line of bone and tooth whispered of transition. What Dart saw was a creature in between, but not in the simplistic missing link sense that the world still craved. It was not half man, half ape. It was something else entirely, a species that had long ago taken its own evolutionary path, part of a branching experiment that would eventually lead to us. In many ways, Dart's interpretation was ahead of its time. He envisioned evolution not as a ladder but as a tree, one with deep African roots. Yet in the 1920s, that idea struggled to survive. The Piltdown fossil still dominated textbooks, convincing generations that the first humans must have been big-brained and European. For nearly 2 decades, Australopithecus africanus was largely ignored. Dart's paper lay unread on shelves, cited mostly as an oddity. The scientific establishment's scepticism was fortified by distance, prejudice, and a simple lack of comparative fossils. To many scholars, Africa remained a blank spot on the evolutionary map, a place of speculation rather than science. And yet, the rock did not lie. In time, others began to look again. Among them was Robert Broom, an older Scottish-born doctor who worked in South Africa, and who, unlike many of his peers, took Dart's ideas seriously. Broom visited Taung, studied the fossil, and concluded that Dart had been right. He began to scour the caves of the Transvaal for more evidence, convinced that if one Australopithecine existed, there must be others. His discoveries in the late 1930s would finally vindicate Dart, but that is another story. What matters here is the turning point, a child's skull that quietly challenged half a century of arrogance. The Taung child, as it became known, revealed that the path to humanity began not with intellect but with adaptation. We did not think our way upright. We walked our way into consciousness. The brain followed the body, not the other way around. That single insight reshaped how scientists thought about our origins. It hinted that our evolution was not a story of steady progress toward perfection, but a series of experiments, each solving the problems of its time. Today, nearly a century after Dart's discovery, the Taung child remains one of the most important fossils ever found. Its features are now understood as belonging to a genus of early hominins, that thrived in Africa millions of years ago. But even stripped of all the classifications that would come later, the fossil still speaks to something deeper: the humility of evidence, the quiet insistence of fact over faith. Dart was not infallible. His later ideas about violent killer apes would fall out of favour. But on that one point, that our roots lay in Africa, in creatures with small brains but human posture, he was right. It is difficult to imagine the isolation Dart must have felt in those years. Surrounded by scepticism, he held on to a conviction drawn not from ideology but from observation. His letters reveal a man both passionate and cautious, aware that the fossil's significance could be mistaken for ego. "It is not the man who is important," he wrote, "but the evidence that he reveals." In that humility, Dart embodied the best of scientific spirit, the willingness to be proven wrong, the patience to wait for vindication by time. In hindsight, the resistance he faced tells us as much about ourselves as it does about the fossil record. Science, though built on skepticism, can still cling to comforting myths. The Piltdown man had seemed noble and European, the product of reason. The town child was small, African, and unthreatening, and for many that made it harder to accept as kin. The rejection of Dart's discovery was not purely scientific, it was cultural. It reflected the same blindness that had shaped the Piltdown hoax decades earlier. The tendency to confuse human worth with human origin. But evidence has a way of enduring. The Tong skull, encased in limestone, had survived millions of years of geological upheaval. It could survive a few decades of academic disdain, and when its time came, it would reshape the map of human evolution, turning attention at last toward the continent that had been dismissed for so long. Dart could not have known it then, but the child from stone would eventually silence the ghosts of Piltdown and rewrite the story of where we began. In museums today, the replica of the Tang child rests quietly under glass. Visitors rarely notice how small it is, scarcely larger than an orange, or how much history it carries in its delicate form. The fossil's face still bears that faint, almost human expression that first startled Dart, an expression caught forever between curiosity and innocence. It is a reminder that the story of human evolution is not one of grandeur, but of persistence. We come from creatures that adapted, stumbled, and endured. The miracle is not that we became intelligent, but that we kept walking. Could a small skull from South Africa undo half a century of arrogance? In the end, it did more than that. It replaced pride with perspective. It showed that truth often arrives not as thunder, but as a whisper in stone, and that, as far as we can tell, is what the evidence shows so far. Why did it take the world so long to believe Africa was our cradle? It was not for lack of evidence, but for lack of imagination. By the time the 1930s arrived, Raymond Dart's town child had already spent a decade in exile from mainstream science, quietly waiting for the world to catch up. It would take another man and another generation of fossils to make people look south again. That man was Robert Broom, a physician turned fossil hunter who shared Dart's heretical belief that humanity's roots were not European nor Asian, but African. Broom was eccentric even by the standards of his time. He carried fossils in his pockets and a revolver in his coat, claiming both were tools of science. In the caves of South Africa's Transvaal region, he began to find skulls and bones that echoed Dart's discovery, but belonged to adults, not children. The most famous came from a site called 𝐓𝐈𝐌𝐿𝐿, where he uncovered an adult skull with a small brain but unmistakably human-like teeth and pelvis. Here, at last, was proof that Dart's little fossil was not a fluke. This adult too walked upright. Broom named it Australopithecus transvaalensis, and later accepted that it belonged to the same species as Dart's find, Australopithecus africanus. Yet even as the fossils multiplied, acceptance came slowly. The idea that small-brained, ape-like beings in Africa could precede Europe's so-called advanced fossils clashed with deep cultural prejudice. Many European scientists still clung to the myth of the March of Progress, the comforting image of humanity rising from bestial darkness toward enlightenment, a march that, in their minds, naturally began somewhere north of the equator. The fossils from Africa did not fit that picture. They were inconveniently old, inconveniently small, and inconveniently African. But Africa was patient. In the 1940s, Broom discovered another set of fossils at Kromdraai. Creatures with massive jaws, thick enamel, and chewing muscles so large that their skulls flared like helmets. They were clearly related to Australopithecus africanus, but far more robust, as if evolution had taken one branch and turned it into a specialist grinder of hard foods. He called them Paranthropus robustus. They were not ancestors of modern humans, but cousins, evolutionary experiments that had thrived and vanished long before us. To Broom, this diversity confirmed that Africa was not just a stage for early humans, but a whole evolutionary workshop, filled with failed designs and adaptive marvels. The fossils, however, could not speak for themselves. They needed champions. After Broom's death in 1951, new voices took up the cause, Louis and Mary Leakey, whose names would become synonymous with the story of human origins. Their search began in East Africa, far from the limestone caves of the south. In the 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 gorge of Tanzania, the Leakeys spent decades sifting through layers of volcanic ash and ancient lakebed sediments, enduring heat, dust, and the long silences of science. For years they found little that would change the debate. But in 1959, Mary unearthed a skull so striking that it changed everything. It belonged to a species unlike any found before, a creature with a small brain but massive jaws and teeth built for crushing. Louis named it Sahelanthropus boisei, the man from East Africa, though today it is known as Paranthropus boisei. Its age, more than 1 million years, shattered the old European timeline and firmly planted the earliest chapters of human evolution in African soil. When the news reached the wider world, even skeptics began to waver. The same year, improved dating techniques began to refine the ages of fossil sites. Volcanic tuffs at 𝐓𝐈𝐿𝐿𝐼 allowed scientists to measure time with new precision, revealing that these early species were far older than anyone had imagined. What had once been dismissed as provincial curiosities now formed the backbone of human history. The centre of gravity shifted southward, from London drawing rooms and Paris salons to the red dust of African valleys. The discoveries kept coming. In 1960, the Leakeys uncovered stone tools near the bones of another hominin, smaller, more delicate, and clearly different from the heavy-jawed Paranthropus. This species, they proposed, was the maker of the tools, a true ancestor of modern humans. They named it Homo habilis, the handyman. Its presence alongside Paranthropus in the same layers revealed a truth that the old linear model could not explain. More than one type of early human had lived in Africa at the same time. Evolution was not a single chain of improvement, but a tangle of overlapping lives. By the 1960s, even the most stubborn resistance began to crack. The fossils, the tools, the dates, they all pointed in one direction. Africa, not Europe or Asia, was the birthplace of humanity. What had once been an unthinkable hypothesis became scientific consensus. The old Eurocentric narratives, shaped as much by politics as by data, gave way to a new map of human ancestry rooted in the southern hemisphere. The phrase, "out of Africa," would later become famous in genetic studies, but its first meaning was simply this: our story began there. Still, it is worth remembering how long the journey from doubt to belief took. For nearly half a century after Dart's discovery, the scientific establishment had clung to a comfortable illusion. It was not evidence that was lacking, but willingness to see what the evidence implied. Prejudice, pride, and the inertia of established thought are powerful forces. The fossils of Africa had to be louder, more numerous, and more undeniable than any found before to change the story. In hindsight, the irony is almost poetic. The continent long dismissed as primitive turned out to be the one that made us human. Every fossil dug from its soil told the same quiet truth, that intellect, culture, and civilization were not gifts bestowed upon a chosen land, but the result of millions of years of adaptation shared by all. The tools of 𝐓𝐈𝐿𝐼 and the bones of Sterkfontein were not symbols of savagery, but of invention. They showed that curiosity, that restless urge to shape stone, to experiment, to survive, had always been our birthright. For the scientists who followed, the shift was not just academic. It changed how we saw ourselves. The human story was no longer the triumph of one region or race. but the shared legacy of a species that began in one place and wandered everywhere. In the 1960s, the Leakey's discoveries made their way into textbooks, museum exhibits, and even popular imagination. For the first time, the phrase African genesis entered public language. It felt both humbling and unifying. Standing at Olduvai today, you can still see the layered cliffs that recorded millions of years of environmental change. The same wind that once carried the dust of Paranthropus now brushes across excavation trenches and tourist hats alike. The place is eerily silent except for the occasional call of birds, and yet it hums with meaning. Beneath that ground lies the deep memory of movement, adaptation, and survival. The story of us before we knew we were us. The acceptance of Africa as our cradle was not the triumph of one discovery, but of accumulation, skull by skull, stone by stone, layer by layer. It was science at its most stubborn and most beautiful, the slow erosion of certainty by fact. And though the work of Broom, Dart and the Leakeys closed one chapter of ignorance, it opened many more of wonder. Africa had not just answered back, it had begun to speak with authority. And perhaps that is the greatest irony of all. The same world that once denied Africa a place in the human story now turns to it for answers about every beginning that matters, about walking, tool-making, family and thought itself. The cradle, it turns out, was never empty. We simply weren't listening, and that, as far as we can tell, is what the evidence shows so far. What happens when evolution stops marching and starts branching? For nearly a century, the human story had been drawn as a single line, a proud ladder rising neatly from ape to man, rung by rung, each fossil ancestor sitting squarely between the last and the next. It was a comforting image, easy to teach, easy to picture, and utterly misleading. By the middle of the 20th century, science began to outgrow that illusion. The fossils themselves, silent but stubborn, refused to fit the ladder. They overlapped, contradicted, and tangled. They showed faces that seemed too young in time and bodies that seemed too old in form. Evolution, it turned out, was not a march, but a mess. A tangle of paths that crossed, split, and sometimes disappeared. The first cracks appeared in the 1930s and 40s, when the discoveries of Robert Broom and the Leakeys began to show that multiple kinds of early humans had lived side by side. There was Ardipithecus africanus, small, upright and lightly built, and Paranthropus robustus, its heavier, more muscular cousin. Both clearly walked upright, both clearly used their hands with skill, and both clearly existed at roughly the same time. The neat ladder that once rose from ape to man suddenly split into two steps at once. Which was the real ancestor, and which was the evolutionary detour? The old diagrams could not answer. To the scientific imagination of the time, this was unsettling. For decades, evolution had been taught as a chain of progress, a moral ascent as much as a biological one. The March of Progress diagram, born in the mid-20th century, became its perfect symbol. A straight file of creatures, each a little taller, a little more upright, until modern humanity stood at the front, proud and alone. But as fossil after fossil refused to fall neatly into line, scientists began to realize that the image was not only simplistic, it was wrong. Species did not transform directly one into another like beads on a string. They branched, diverged, and sometimes rejoined. Most branches ended, their experiments extinguished. A few endured. The human lineage, far from being a ladder, was a thicket. By the 1950s, the field of systematics, the science of classification, was undergoing its own revolution. Biologists such as Ernst Mayr and George Gaylord Simpson began to rethink how species should be defined and how their relationships should be drawn. Instead of ranking creatures by how advanced they appeared, scientists began to reconstruct their shared ancestry. The result was the phylogenetic tree, a branching diagram that mapped descent, not hierarchy. Each split represented a common ancestor giving rise to two lineages. Some survived and diversified, others dwindled and vanished. It was a model born from humility, one that placed all life, humans included, on equal footing as participants in evolution's continuous experiment. When applied to the human story, This new way of thinking changed everything. It allowed researchers to see Paranthropus not as a failed version of us, but as an independent lineage that had solved its own problems in its own way. Its wide face and massive chewing muscles were not primitive defects but adaptations, an answer to a specific diet and environment. The species was not a rung below us on the ladder, but a branch beside us on the tree. It lived, thrived, and then disappeared, its legacy buried in the African soil. This perspective also reframed the meaning of extinction. In the old ladder model, extinction seemed like failure, the fall of a lesser form on the way to something higher. But in a branching model, extinction is simply part of the process. Most species that have ever lived have gone extinct. It is the rule, not the exception. Survival, in that light, is not destiny but accident, the outcome of adaptation meeting circumstance. Our lineage, like any other, just happened to find a niche that worked. The ladder had implied purpose, the tree suggested contingency. The shift from ladder to tree was not just a matter of diagrams, it reflected a deeper change in how scientists, and by extension humanity, understood itself. The ladder was a symbol of human exceptionalism, of progress marching toward perfection. The tree was democratic, almost humbling. It showed that we were one branch among many, part of a tangled bush of life that had been pruning and reshaping itself for billions of years. It erased the illusion of inevitability. There was no single path leading to us, no grand design. There were only branches that survived long enough to leave a trace. The fossils of the mid-century reinforced this view with frustrating consistency. In South Africa, Broom's Australopithecines overlapped in time with the robust forms. In East Africa, the Leakey's finds reveal that Homo habilis had shared its world with Paranthropus boisei. Even as the first tools appeared, the world was still crowded with other ways of being human. For every adaptation that worked, a dozen others were tried and abandoned. The tree was sprawling, not linear. This new model also forced science to confront its language. Words like primitive and advanced began to lose their meaning. A chimpanzee is not a primitive human, nor are humans advanced chimpanzees. Both species are modern. Both have been evolving for the same span of time since their split from a common ancestor millions of years ago. The notion of progress in evolution gave way to the concept of adaptation, the idea that every organism, in its own context, is perfectly suited to the demands of its world. Even extinction, viewed through this lens, is not failure but change at work. Still, the idea of the tree was not easy for everyone to accept. The human mind craves order, and the tree, with its messy intersections and abrupt endings, offered anything but. In museums and textbooks, the old march of progress image persisted, partly because it was simple, partly because it flattered us. It told a story we wanted to hear, that evolution had been leading somewhere, and that somewhere was us. The tree, by contrast, whispered that we were just lucky. It was less comforting, but more accurate. By the late 1950s and early 60s, the tree model had fully taken hold in paleontology. Scientists began to speak not of the missing link, but of common ancestors and sister lineages. The language of gaps gave way to the language of relationships. The focus shifted from seeking the perfect transitional fossil to understanding variation across time. Each discovery added not a step but a branch, another clue to how life experimented, diverged, and sometimes converged again. This branching model also redefined how fossils were interpreted. When Louis Leakey's team found Paranthropus boisei at 𝐓𝐈𝐌𝐿𝐄𝐒𝐒, they did not treat it as a direct ancestor, but as a cousin. The same was true of Australopithecus africanus and Paranthropus robustus. These species were close to the line that led to Homo, but not on it. The realization that multiple hominin species had coexisted meant that evolution was not a story of one species turning neatly into the next, but of overlapping experiments, parallel lives sharing the same landscapes, competing and sometimes even cooperating for the same resources. If the ladder was a tale of inevitability, the tree was a story of chance. It emphasized how geography, climate, and luck shape outcomes. A drought might favor one branch, a volcanic eruption might erase another. The rise of Homo habilis or Homo erectus was not foreordained. It was one result among many possible ones. This idea humbled science. reminding researchers that they were reconstructing history not from a script, but from scattered fossils and probabilities. As the tree grew in scientific thought, so did its implications beyond biology. Philosophers and theologians grappled with its message. The ladder had offered a comforting symmetry, humanity as the pinnacle of progress. The tree, by contrast, suggested that we were simply one twig on a vast living structure, transient, contingent, and no more or less meaningful than any other. It was a shift from a story of ascent to a story of interconnection. We were not above nature, but within it. The dead ends of evolution, species like Paranthropus or Australopithecus sediba, that later proved not to lead to modern humans, became central to this understanding. Each was a reminder that nature is prolific, not purposeful. Every fossilized branch represents a way of life that once worked until it didn't. These extinct cousins tell us as much about what it means to be human as our direct ancestors do. They reveal the variety of solutions evolution has tested and the fragility of the one that survived. It is difficult to overstate how revolutionary this conceptual shift was. It did not merely redraw our family tree, it redefined the very meaning of ancestry. The idea that our lineage had siblings, species that thought, walked, and lived alongside us, only to vanish, made the human story both richer and lonelier. The tree was no longer a triumphant climb, but a record of loss and persistence. Even today, when we look at the branching diagrams of human evolution, with their dense intersections and uncertain lines, we are seeing the mid-century's intellectual transformation made visible. Each split is a hypothesis, each dotted line a reminder of how much we still do not know. The ladder has vanished, replaced by something far more alive, a network of possibility. And yet, if you stand back from that tree and look at it not as a scientist but as a human being, the picture it paints is strangely comforting. Evolution, seen this way, is not about competition or conquest, but about resilience. Every branch, successful or not, represents life trying, reaching, adapting, persisting. We are one of those branches. For now, we're still here. What happens when evolution stops marching and starts branching? It gains depth, humility, and truth. The tree does not point upward, it spreads outward. It reminds us that survival is not the same as destiny, and that progress is an illusion born of short memories. The story of life is not a race to the top, but an endless unfolding, each branch a whisper of what could have been. And that, as far as we can tell, is what the evidence shows so far. What did the double helix reveal about our real relatives? For more than a century, bones had been the only witnesses. Fossils, stone tools, and fragments of skulls told a story written in dust and patience. But in the middle of the 20th century, a new kind of evidence began to speak. One that came not from the earth, but from within us. In the spring of 1953, two young scientists at Cambridge University, James Watson and Francis Crick, built a model that would reshape every field from medicine to anthropology. The structure was simple, elegant, and shocking in its implication. A twisted ladder of paired molecules that carried the code of life itself. DNA, the double helix, was not only the key to heredity, it was also the first real chance to measure the invisible history of evolution. Until then, the connections between species were mapped by anatomy. Skulls compared, bones aligned, shapes measured. It was a science of surfaces, meticulous but limited. The double helix made it possible to look beneath those surfaces, to trace ancestry not through what bodies looked like, but through the code that built them. The molecules in our cells turned out to be more honest than fossils. They kept time with quiet precision, mutating at rates that could be measured and compared. Where bones stopped, DNA continued the story. At first, few imagined that this discovery could reach back millions of years. The early excitement around the helix focused on disease and genetics, not prehistory. But as the techniques improved, from protein sequencing to the first crude comparisons of genetic material between species, the implications grew. By the late 1960s, scientists like Vincent Sarish and Alan Wilson at Berkeley had begun to calculate the rate of molecular change by comparing proteins shared by different primates. Their results were startling. They suggested that humans and African apes had diverged far more recently than anyone had guessed. Not tens of millions of years ago, as textbooks claimed, but only around 5 to 7 million years in the past. The reaction was disbelief. For decades, many anatomists had placed our split from apes deep in the Miocene, some 20 million years earlier. The fossil record seemed to show a long separation, a story of gradual ascent. But the molecular data told a different tale, a sudden, intimate divergence. Humans, chimpanzees and gorillas, the data implied, were close relatives, not distant cousins. We had been sharing ancestors until shockingly recently in geological time. The logic behind the method was simple but profound. Every living organism carries mutations, small random changes that occur as DNA is copied. Over generations, these changes accumulate like ticks on a clock. If two species share a common ancestor, the number of genetic differences between them roughly corresponds to the time since they split apart. By measuring those differences and calibrating them with known fossil ages, scientists could estimate when lineages diverged. This became known as the molecular clock. The molecular clock was far from perfect, but it was revolutionary. It gave anthropology its first quantitative way to measure evolutionary time. It also stripped away the last traces of romantic hierarchy that had survived from earlier centuries. DNA did not care about pride or progress. It showed that humans and chimpanzees share roughly 98 to 99% of their genetic code, a level of similarity closer than that between many species of birds or rodents. The gap between human and animal was no longer philosophical. It was measurable and small. The implications rippled far beyond science. The old ladder of progress, already replaced by the branching tree, was now revealed as something even more intricate, a molecular network connecting every living thing. The tree of life was no longer drawn from fossils alone. It was written into the alphabet of the cell. For the first time, scientists could compare not just bones but genes, tracing relationships across the entire spectrum of life, from bacteria to mammals. Humanity's place in nature was no longer a matter of belief. It was a matter of sequence. But not everyone welcomed that conclusion. In the 1970s and 80s, debates raged over the validity of the molecular clock. Critics argued that mutation rates varied too much between species to serve as reliable timers. Others pointed out that calibration still relied on fossils, the very record the method was supposed to transcend. And yet, even with its flaws, the clock kept ticking. Each new method, from protein electrophoresis to mitochondrial DNA sequencing, refined the picture. The human-chimpanzee split consistently landed between 5 and 7 million years ago. No other line of evidence contradicted it. As molecular biology advanced, so did technology. The 1970s brought gel electrophoresis, allowing scientists to separate and visualize DNA fragments. The 1980s brought polymerase chain reaction, PCR, a technique that could copy even the tiniest trace of genetic material billions of times. What had once required grams of tissue could now be done with a single cell. Suddenly, evolution could be read not only in living species, but in the ancient remains of extinct ones. A new kind of archaeology began, one of molecules instead of stones. In anthropology, the shift was seismic. For the first time, researchers could compare living primates at the genetic level, confirming relationships that morphology had only hinted at. Gorillas were shown to be our next closest relatives after chimpanzees and bonobos. Orangutans, long thought to be near kin, were placed farther back in the tree. The great apes of Africa and humans formed what biologists called a clade, a single, tightly related branch of the primate family. We were not an exception to nature. We were an extension of it. This genetic convergence also forced science to rethink what it meant to be human. If the difference between us and a chimpanzee was only a few percentage points of DNA, then what made the gap feel so vast? The answer, scientists realized, was not the number of genes, but how they were used. Tiny shifts in timing, regulation and expression, when certain genes turned on or off during development, could produce enormous differences in form and behavior. The complexity of the human brain, the shape of our pelvis, even the subtle structure of our hands could be traced to small genetic adjustments, not wholesale invention. Evolution had not rewritten the book of a life. It had edited it. By the 1980s, DNA evidence had become so overwhelming that the old debates over our kinship with apes began to fade. Museums that once displayed the march of progress quietly updated their exhibits. The new diagrams showed humans, chimpanzees and gorillas branching from a common ancestor, their lines drawn close together. The story was no longer one of isolated grandeur but of shared history. The emotional shock of that realization, that we are not only descended from apes but remain one, was difficult for culture to absorb even as science moved on. In the background of this revolution, another profound shift was taking place. The same molecular techniques used to compare species were being applied to populations within our own. Researchers began sequencing mitochondrial DNA, the small, maternally inherited genome found in every cell, to trace the movement of human groups through time. Though that work would later lead to the idea of a common African origin for modern humans, in these early decades it served a simpler purpose: to remind us that our diversity is recent and our relatedness profound. The double helix had united the living world in one sweep of chemistry. It had also united us with each other. It is easy to forget now how radical this was. For generations, science had defined humanity by its differences, the things that set us apart from the natural world. The double helix inverted that perspective. It showed that what unites us is far greater than what divides us, not just among ourselves, but with every other species. The molecule that builds a tree also builds a person. The instructions that form a whale's heart are written in the same biochemical language as those that form a human brain. The code is universal. Only the punctuation changes. Looking back, the discovery of DNA was less an invention than a revelation, an unveiling of something that had always been there, waiting to be read. The fossils had given us a story in fragments. Genetics turned it into a language. It confirmed, with quiet certainty, what Darwin had intuited without ever knowing the molecule's name, that all living things are variations on a single theme. By the end of the 20th century, the genetic revolution had rewritten the foundations of anthropology. The fossil record remained indispensable, but it was no longer the only witness. DNA had become the new Rosetta Stone of life, translating the deep history of species into measurable sequences. Where bones ended, molecules began, and with every new sequence compared, the illusion of human uniqueness grew thinner. Yet even in this precision, there was humility. The more we learned about the genome, the more we realized how much we still did not understand. The double helix was no simple ladder, but a vast dynamic text, full of edits, repetitions, and forgotten instructions. For all our advances, the essence of life remained mysterious, not in a mystical sense, but in a scientific one. Each discovery only deepened the question of how complexity arises from simplicity, how consciousness grows from chemistry. What did the double helix reveal about our real relatives? That there are no missing links, only continuous threads. That every living thing on Earth, from bacteria to humans, shares ancestry deeper than any fossil can show. And that our closest cousins are not lost in prehistory. They are still here, looking back at us from the forests of Central Africa, their DNA nearly identical to ours. For all its technical brilliance, the genetic revolution did something profoundly simple. It brought us home. It reminded us that the story of life is one story, told in many dialects of the same molecular language. And in that quiet realization, something ancient and humbling reawakened. The knowledge that we're not apart from the world, but part of its single, unfolding experiment. And that, as far as we can tell, is what the evidence shows so far. What did the world look like at the exact moment humans and chimpanzees parted ways? To find that moment, you have to go back around 7 million years, to a world that would be almost unrecognizable today. The continents sat roughly where they do now, but the climates that shaped them were shifting in ways that would transform life forever. Africa, still the great engine of mammalian evolution, was in the middle of one of its slow, rhythmic contractions. Forests retreating, grasslands advancing, rainfall growing less predictable with every passing millennium. The lush, humid canopies that had once stretched unbroken from coast to coast were beginning to fragment into a mosaic of woodlands, river corridors, and open savannas. And somewhere in that patchwork, Among the figs and thorn trees, a population of ancient apes was starting to change the way it moved. The late Miocene was a time of restlessness, both geological and biological. The African plate was cracking and lifting, forming the great rift valleys that would one day cradle the fossil beds of Ethiopia, Kenya and Chad. Volcanic forces reshaped the landscape, raising mountains that caught moisture and created local climates of their own. As the highlands rose, the rainfall patterns shifted. Where once there had been dense rainforests, now there were broken woodlands and seasonal grasslands. Lakes appeared and vanished in cycles that spanned tens of thousands of years. It was a world in motion, an Africa of thresholds rather than boundaries. The creatures that lived there were also in transition. The forests still held familiar shapes, monkeys leaping through branches, small antelopes browsing in the undergrowth, early elephants lumbering through clearings. But something subtle was happening in the apes. They had once been fully at home in the trees, their long arms and grasping feet perfectly suited to an arboreal life. Yet as the forests thinned, the ground began to matter more. On the forest edges, between the light and the shade, natural selection was testing a new experiment in movement, standing upright, even if only part of the time. It is tempting to imagine this shift as a single step. One moment of revelation when an ape straightened its back and became something new. But evolution does not work in moments, it works in tendencies. Over hundreds of thousands of generations, some apes found themselves moving more frequently on the ground, gathering fallen fruit, crossing open patches between trees, scanning for predators. Those that could balance better, free their hands, or cover more distance in less time had an advantage. Bipedalism was not a conscious decision. It was a series of small accidents that happened to pay off. 7 million years ago, the world was warmer than today, but the temperature was falling slowly, part of the long cooling trend that would culminate in the ice ages. The carbon dioxide levels were dropping, and with them, the global forests. Africa was drying. The Sahara had not yet become a true desert, but its early bones were forming, expanding belts of scrub and grass stretching northward. In the central regions, the woodlands were breaking into patches, connected by rivers that swelled in the rainy seasons and shrank into ribbons during the dry months. Life was organised around water, as it always had been, but now survival depended increasingly on the ability to travel between oases of shade and food. At this scale of time, what we call the split between humans and chimpanzees was not a single event. It was more like a drawn-out divergence. Populations of ancestral apes spreading across Africa, separated by geography, climate and chance, slowly accumulating differences. One group, perhaps isolated by a widening rift valley or a shifting river system, adapted more to the open woodlands. Another stayed within denser forest belts, retaining the climbing lifestyle. Over thousands of generations, gene flow between them weakened, and their paths began to drift apart. At some point they stopped being able to interbreed, not because of a sudden change, but because of slow genetic distance. From that subtle divide came two fates, one leading toward the chimpanzees and bonobos of today, the other toward us. The earliest part of that journey remains one of the great mysteries of paleoanthropology. The fossil record for this time is frustratingly sparse. Bones decay quickly in humid forests, and the geological upheavals of the rift have buried or destroyed much of what once existed. But even without the fossils, the environment itself tells a story. Ancient pollen, isotopes in soil carbon, and the chemistry of preserved teeth from other mammals all reveal the same pattern. Forests were giving way to open habitats, and species were responding in kind. Herbivores adapted to graze tougher grasses, predators followed them. And in the midst of that ecological reshuffling, some apes began experimenting with a new balance between trees and ground. If you could stand there, on the margins of a Miocene riverbank at sunrise, the world would feel both familiar and alien. The air would be heavy with humidity, filled with the calls of hornbills and the low rumble of distant elephants. You might see early antelopes wading in the shallows, crocodiles waiting just beneath the surface, and troops of monkeys crossing overhead through the thinning canopy. On the ground, a band of apes moves cautiously through the tall grass, pausing upright to look around. Their spines are straighter than their ancestors, their hands free enough to carry fruit or stones. They are not yet human, not yet even fully committed to walking, But evolution is in motion. The idea of uprightness has entered the genome. What drove this change has been debated for decades. Some argue it was climate, that as the forest vanished, apes were forced into the open, where standing upright helped them see over grass and stay cool in the sun. Others point to foraging, suggesting that reaching for fruit on low branches or carrying food required new postures. Still others think it began as a way to wade through shallow water. The truth may include all of these and none of them. Evolution does not follow a single logic, it follows opportunity. What matters is not why bipedalism began, but that it began when it did, a few million years after our lineage split from that of the chimpanzee. That divergence also reshaped behaviour. The forests offered security but little visibility. On the ground, dangers multiplied. Large cats hunted the edges, and crocodiles ruled the rivers. To survive, early apes would have needed new strategies: group cooperation, vigilance, communication. Perhaps the seeds of social intelligence, too, were already forming in these mixed habitats. To live between forest and plain is to be both vulnerable and adaptable, two traits that would come to define our lineage. The landscapes of this period also nurtured some of the earliest experiments in tool use. We cannot say when the first ape picked up a stone to crack a nut or strip bark, but many modern primates still perform such behaviours. It is not difficult to imagine that similar acts were already taking place millions of years earlier. The transition to life on the ground would have increased both the need and the opportunity to manipulate the environment, to dig, to open, to carry. Even if those gestures were crude, they laid the groundwork for the tool-making traditions that would emerge much later. The global context of this transformation was immense. The Indian subcontinent had long since collided with Asia, raising the Himalayas and altering global wind patterns. The Mediterranean was drying, a preview of the environmental volatility that would later define the Pleistocene. The oceans cooled, currents shifted, and the African monsoon system wobbled. These were not gentle changes. They were upheavals in slow motion, and every species on Earth was caught in their pull. The split between humans and chimpanzees was one small ripple in that vast rearrangement, a localized experiment that would echo through time. 7 million years is a difficult distance to imagine. It is not deep enough to erase the shapes of the continents, but long enough to erase almost everything that lived. The apes who stood on those Rift Valley shores are gone, their bones turned to dust, their forests transformed into dry scrub, and yet something of them remains in us. Not as memory, but as architecture. Every time we balance on two legs, every time we walk across an open space, we repeat the same evolutionary gamble they once made. Standing upright was a risk, and it paid off just enough for the lineage to continue. The beauty of this moment lies in its ambiguity. We do not know exactly when or how the split occurred, nor can we trace a single ancestral pair that marks it. The fossil record will always be incomplete, and the genetic record, though precise, can only point to a range of possibilities. Somewhere between 5 and 7 million years ago, in a landscape of trees and grass, one population of apes drifted one way, and another drifted another. From then on, their stories would run parallel, reflecting each other in strange and familiar ways. It is humbling to realize that the difference between a human and a chimpanzee, the difference that eventually led to art, language, and science, began with changes so subtle they were invisible at the time. A slightly altered pelvis, a more stable spine, a habit of glancing upright just a little longer. Evolution did not set out to create intelligence, it simply explored balance. Out of that balance came perspective, literally and figuratively. To stand is to see differently. To walk is to wander, and once the wandering began, it never stopped. What did the world look like at the exact moment humans and chimpanzees parted ways? It looked like Africa caught between two climates, its forests whispering their last dominance, its savannas still young and restless. It looked like an ordinary world filled with extraordinary possibilities. From the trees to the grasslands, from the shadow to the sun, the path forked quietly without witnesses, and the long story of us began to diverge. And that, as far as we can tell, is what the evidence shows so far. Could a single skull from the sands of Chad be standing at the fork of all humanity? That is the quiet question that has lingered ever since a small team of scientists brushed dust from a weathered cranium that looked too old, too strange, and too important to fit easily into any known story. They called it Tumai, hope of life in the Dazaga language, a name given to children born at the end of the dry season, when survival feels most precarious. And somehow, that name fit. In the year 2001, a team led by Michel Brunet from the University of Poitiers ventured into the Durab Desert in northern Chad. It was not the kind of place most would expect to find the roots of humanity. The region lay more than 2,000 kilometres from the famous Rift Valley sites that had dominated paleoanthropology for decades. It was flat, searingly dry, with nothing but rippling sand and the occasional dune. But Brunet and his colleagues believed that under the desert's surface lay the ghosts of a greener world, one that had once supported lakes, forests, and early mammals. They were looking not for fame, but for fossils of ancient vertebrates that could fill gaps in Africa's evolutionary record. What they found instead would challenge every neat boundary in human origins. Among the scattered bones of ancient animals, fish, crocodiles, antelopes, one fossil stood apart. It was a nearly complete cranium, distorted but unmistakably primate. Its brow ridges were massive, its face short and tucked in, and its brain case small, no larger than that of a modern chimpanzee. Yet the base of the skull, the way it joined to the spine, looked oddly human. The team named the species Sahelanthropus tchadensis, the Sahel human from Chad. By geological dating of the surrounding sediments, it appeared to be about 7 million years old, placing it near the exact window when genetic studies had predicted that humans and chimpanzees last shared a common ancestor. At first glance, Tumai seemed almost mythical, as though evolution had conspired to produce a fossil exactly where and when scientists most needed one. The skull's age and anatomy appeared to straddle the Great Divide. Its small canine teeth lacked the dagger-like shape seen in apes, and the face was relatively vertical, without the projecting muzzle typical of chimpanzees or gorillas. The base of the skull, the foramen magnum, seemed to point downward rather than backward, a trait associated with upright posture. This detail alone suggested that Tumai might have walked on 2 feet, not 4, hinting at one of the earliest experiments in bipedalism. But as with all stories in human evolution, the more light you shine, the more shadows appear. The reconstruction of the skull was complicated. It had been crushed, warped by eons of sediment pressure. Different research groups produced different digital reconstructions, each subtly altering how the neck would attach, and therefore how upright the head might have been. Was the foramen magnum truly positioned like that of a biped, or was it simply intermediate between apes and later humans? Without postcranial bones, no one could be certain. For several years, the debate remained suspended in that limbo of scientific caution. The fossil's discoverers held firm that Sahelanthropus tchadensis was the earliest known member of the human lineage, predating all other candidates and representing a creature already experimenting with walking upright. Others were less convinced, pointing out that some of its features, particularly the shape of the brow and the size of the brain, fell comfortably within the range of early chimpanzees. Some went further, suggesting it might belong to the ape line entirely, a species close to the shared ancestor, but not part of our own family branch. Then came the femur, or rather, the mystery of the femur that no one talked about. In the mid-2000s, rumours began circulating of a thigh bone found near the original Tumai site. It had been collected at the same time as the skull, but remained unstudied, sitting quietly in storage in France. For years, its significance hovered over the debate like a ghost. A femur could answer the question that the skull could not. Was this being a habitual biped, or still a tree-dweller? When a graduate student at Poitiers reportedly rediscovered the bone and showed it to her supervisors, the internal disagreement spilled into public view. Some researchers claimed that its anatomy resembled that of a knuckle-walking ape, not a bipedal hominin. Others insisted that without a full reconstruction, any conclusion would be premature. In 2020, after nearly 2 decades of speculation, a study describing the femur was finally published. Its authors argued that the bone's shape and muscle attachment suggested limited or no habitual bipedality, that Sahelanthropus was primarily a climber, not a walker. But the story did not end there. Only 2 years later, another group reanalyzed the original fossils, including fragments of arm bones and an ulna that had previously been ignored. Their conclusions swung the pendulum back again. The evidence, they said, was compatible with both bipedal walking and tree climbing. The old pattern returned. For every argument in human evolution, there is always another. Beneath the anatomical disputes, a deeper question remained. What did it mean that this fossil came from Chad? Nearly every major discovery of the early hominins had come from East or South Africa. That was the established map of origins, reinforced by the Rift Valley's convenient geology. Its sediments preserved bones, and its layers recorded time like the pages of a book. But Sahelanthropus emerged from the centre of the continent, from a region not known for hominins at all. Its presence there suggested something profound, that our ancestors, or their close relatives, were not confined to one corner of Africa, but roamed widely across its ancient habitats. During the late Miocene, the region that is now the Jurub Desert would have looked nothing like it does today. Fossilised fish, turtles and crocodiles show that it once lay near a vast lake surrounded by gallery forests. It would have been a humid, green landscape filled with life, antelopes, pigs, primates and predators. In that environment, Sahelanthropus might have spent its days moving between trees and open patches of forest floor, feeding on fruit and leaves, wary of crocodiles and big cats. Whether it walked fully upright or only occasionally, it was part of a lineage adapting to change. To some scientists, the skull's small brain size, about 350 cubic centimetres, was evidence that walking did not require intelligence, only anatomy. If Tumai was indeed an early biped, it meant that upright posture evolved long before tool use or larger brains, reversing the old assumption that mind came before motion. It also blurred the boundary between ape and human. In this fossil, those labels start to lose meaning. What we see instead is experimentation, nature testing new body plans as environments shifted and forests fragmented. Yet even today, more than 20 years after its discovery, Tumai sits in an ambiguous space in our family tree. The fossil is too old and too unique to compare easily. Its mix of traits resists classification. If it truly represents the earliest branch of the human lineage, then it pushes back the timeline of our divergence, placing bipedality near the root of our family. If not, then it is the closest shadow of that ancestor, an evolutionary cousin whose life mirrored the same challenges our true ancestors faced. In either case, it tells us that the story of becoming human did not unfold neatly or in one place. It was messy, regional, and diverse. There is also a poetic justice in the fossil's name. Tumai means hope of life, but it also reminds us that life's hope often lies in persistence rather than perfection. Whether or not this species stands directly on our lineage, it has already achieved something remarkable. It expanded the map of our curiosity. By looking westward, away from the well-trodden rift, scientists discovered that the search for origins is not about where we expect to find answers, but about where we are willing to look. Standing before the fossil today behind the glass of a museum in N'Djamena, one might feel a strange connection, not just across millions of years, but across all the uncertainty that science must live with. We cannot reconstruct the exact posture of Tumai. We cannot watch it walk, climb, or sleep. All we have is a small skull, a few bones, and the landscape that once surrounded them. Yet that is enough to glimpse a moment when our lineage was still undecided, when the balance between tree and ground was still in play. The hope of life, it turns out, was not about knowing where we came from. It was about continuing to look. Tumai may never be the definitive first human, but it is a symbol of something older and deeper, the way evolution keeps experimenting with form, the way curiosity refuses to stay still. The deserts of Chad, once a green cradle of life, are now barren and silent. But somewhere beneath their sands, the trace of that first step, whether taken or imagined, remains. And that, as far as we know for now, is enough. What if our ancestor walked upright, but still swung through trees? It is a strange image, the idea that the story of walking began not on open plains, but among branches, under a canopy where balance was a matter of survival. In the heart of Kenya's Tugen Hills, where red earth meets green escarpments and the sky opens in vast empty light, scientists once unearthed fossils that suggested just that. They belong to a being named Orrorin tugenensis, the original man. Yet, as always in paleoanthropology, the name was both bold and uncertain, part proclamation, part question whispered through 6 million years of silence. The story began in the year 2000, when a small team led by Brigitte Sanu and Martin Pickford explored the rolling terrain of the Tugen Hills in central Kenya's Baringo district. These hills rise like a geological time machine, layer upon layer of ancient sediments stacked by rivers and volcanoes, recording epochs of climate and evolution. The rocks here are rich in fossils, but most are from the Miocene, when apes flourished in Africa's forests. Seenet and Pickford were searching for traces of creatures that might bridge the gap between those apes and the earliest humans. It was in a place called Lucano, a dry ravine cutting through soft red clay, that the fragments appeared. A piece of jaw with teeth, parts of arm bones, finger bones, and, most tantalizingly, a femur. The bones were small, fragile, but their shape suggested something extraordinary. The thigh bone in particular bore signs of habitual stress along its neck and shaft, the kind of reinforcement seen in creatures that put most of their weight on their hind limbs, yet its upper end curved like that of an ape, designed for climbing. It was a bone caught between two worlds. Dating the site placed the fossils at roughly 6 million years old, just after the estimated split between the ancestors of humans and chimpanzees. That made Orrorin tugenensis one of the oldest known members of the hominin lineage. If the interpretation of its bones was correct, then the capacity for upright walking had already evolved at this early stage, long before the appearance of larger brains, tools, or even the genus Homo itself. The landscape it once inhabited would have been lush and varied. The Tugen Hills of the late Miocene were no dry badlands, but a patchwork of gallery forests, woodlands, and open grasslands threaded by rivers. Fossilized pollen and animal bones from the same strata tell of a mixed environment. Trees for shade and safety, open ground for foraging. Such habitats tend to produce generalists, creatures capable of adapting to multiple ways of life. And Orrorin, it seems, was one of them. The femur of Orrorin remains one of the most debated bones in human evolution. When Seenet and Pickford first analysed it, they noticed the thickened cortical bone along the lower part of the neck, a reinforcement pattern that in modern humans counteracts the compressive forces generated during upright walking. Apes, by contrast, show a more even distribution of bone around the femoral neck, as their locomotion involves hanging and climbing rather than sustained bipedal strides. The conclusion, they argued, was clear. Orrorin walked habitually on two legs, at least when on the ground. Yet the rest of the skeleton told a subtler story. The arms were long and curved, built for climbing and gripping branches. The thumb bones were robust, suggesting dexterity, though far from the precision grip of later humans. The teeth were small, with thick enamel, more like ours than a chimpanzee's, but still shaped for a mixed diet of fruit and tough vegetation. Altogether, Orrorin seemed both familiar and alien, a creature that could balance on its legs when needed, yet retreat to the trees when danger came. If one could have followed it through the forests of ancient Kenya, the sight might have been strange. It may have stood upright while scanning for predators or reaching for fruit, its head swivelling on a neck strong enough to carry the weight of curiosity. But when branches swayed overhead, it likely climbed with ease, using arms honed by millions of years of arboreal ancestry. Its world was not one of clear boundaries between ground and canopy. It was an ecosystem in transition, and its body reflected that ambiguity perfectly. This duality, part groundwalker, part tree-dweller, forces us to rethink what it means to walk. For most of our species' history, we have imagined bipedalism as a revolutionary step, a clean break between ape and human. But Orrorin complicates that narrative. Its existence suggests that the evolution of upright posture may have begun not as a dramatic leap, but as a series of quiet experiments, temporary adjustments to changing environments. Walking upright was not yet a way of life. It was one more tool in a repertoire of survival. The geology of the Tugen Hills offers a backdrop to that transformation. Volcanic ash layers, ancient lake beds, and fluvial sediments record cycles of climate change that oscillated between wetter and drier periods. Around 6 million years ago, Africa was cooling. Forests began to fragment, opening into woodlands. In such conditions, being able to stand and move efficiently on the ground would have been useful, not necessarily to travel far, but to move between trees, to wade through shallow water, to carry food or infants. It was an adaptation of opportunity rather than necessity, a response to a world in flux. For many years, Orrorin was viewed with skepticism by parts of the scientific community. Some researchers questioned the dating, or suggested that the femur's anatomy had been overinterpreted. Others pointed out that other early fossils like Ardipithecus or Australopithecus already provided clearer evidence of bipedalism. But what Orrorin added to the record was time. It pushed the behaviour deeper into the past, hinting that the ability to walk upright did not suddenly appear but evolved gradually, perhaps independently in several early populations. There was a kind of irony in how the fossil was found. For decades, scientists had searched for the so-called missing link, expecting it to look half ape, half human. Orrorin, like Sahelanthropus, showed that evolution does not produce such tidy hybrids. Instead, it leaves mosaics, beings with a patchwork of old and new traits, each adapted to its own moment. To hold the femur of Orrorin is to hold a piece of that mosaic, a reminder that every bone in our ancestry carries contradictions. Its discoverers nicknamed it Millennium Man, a label both symbolic and convenient for headlines. Yet behind the media attention was genuine scientific awe. The fossil record for the period between 7 and 5 million years ago remains incredibly sparse. For that era, each discovery is like a word torn from a lost manuscript. We cannot read the whole sentence, but even fragments can shift the meaning of the story. Orrorin did just that. It introduced a new possibility, that upright walking began among forest dwellers, not grassland wanderers. When viewed in cross-section, the femur of Orrorin reveals a thickened lower cortex precisely where modern humans bear weight. This single anatomical feature has become one of the most discussed pieces of evidence in the field, revisited in endless biomechanical studies. Could similar stress patterns appear in apes that occasionally stand? Could millions of years of compression alter the fossil's shape? The debate continues, and perhaps that is the point. Science is not a contest of certainties, but a conversation with the past. What we can say, as far as evidence allows, is that Orrorin represents a stage when the lines between behaviours blurred. It was not yet committed to a human way of moving, nor bound entirely to the trees. It lived in a world of edges, forest merging into savanna, ape merging into human, four legs merging into two. To call it the original man may be poetic exaggeration, but it captures something true. The sense that this species stood close to a turning point, a hinge of evolution when our lineage began to test gravity differently. If one could stand on a ridge of the Tugen Hills today and imagine the world as it was 6 million years ago, one might see the shimmer of water in the valleys below, smell the wet soil after rain, and hear the faint rustle of branches in a humid wind. Somewhere among those trees, an Orrorin might be climbing, stopping briefly to stand upright, to gaze at a horizon it would never understand. That moment, fleeting, unconscious, was the start of a long chain of balance and bone that would eventually lead to us, and yet, even now we cannot be sure. Was Orrorin truly our ancestor, or merely one of many species exploring similar possibilities? Its fossils are too few to answer. We do not have its skull, only its bones. But what we do have is enough to remind us that evolution is not a straight path. It is a field of intersections, where each step forward leaves behind 1,000 alternate routes. So perhaps Orrorin was not the first of us, but one of the last of its kind, a creature that walked upright in the forest shadows, unaware that the ground beneath its feet was becoming the stage for a new story. And as we trace that story back through time, bone by bone, layer by layer, we find that the question of where we came from has never had a single answer. It only has echoes and footprints that vanish into red earth. Was this gentle tree dweller the closest thing to the real missing link? The fossil that would one day be known as Ardi was not discovered in a triumphant moment of clarity, but in quiet fragments, delicate pieces of bone weathered by time and fragile enough to crumble at a breath. Yet from those fragments, a portrait emerged of a being unlike any other. a creature that stood upright yet still clung to branches, that walked the forest floor on cautious feet, and that may have lived in a world where competition was replaced by cooperation. Her name, Ardipithecus ramidus, means the root of the ground ape, and perhaps, in both name and form, she carries something fundamental about what lies beneath us. The story began in the early 1990s, when paleoanthropologist Tim White and his team from the University of California, Berkeley, were working in the Middle Awash Valley of Ethiopia. The region was already famous for yielding Lucy, the celebrated Australopithecus afarensis, but White and his colleagues were searching for fossils even older, traces of what might connect Lucy to more primitive forms. The landscape was harsh and unforgiving, dry basaltic hills, endless scrub, and shifting winds that erased footprints almost as fast as they were made. But in 1992, while surveying near the village of Aramis, one of White's team members spotted a small fragment of hand bone embedded in volcanic ash. It was ancient. Radiometric dating placed it at around 4.5 million years old. Over the next few seasons they uncovered more bones, teeth, limb fragments, pieces of pelvis, skull and spine. The excavation became an exercise in patience and precision. The fossils were so delicate that each one had to be encased in plaster and painstakingly cleaned under microscopes back in the lab, grain by grain. After years of reconstruction, the skeleton of a female individual began to take shape. She stood about 1 meter 20 tall and weighed roughly 50 kilograms. Light, compact, and strangely familiar. The team called her Ardi, short for Ardipithecus ramidus. At first glance, Ardi looked like a mosaic of contradictions. Her pelvis was short and broad, with features suggesting she could walk upright on the ground. But her hands, long arms, and grasping big toes told another story. She was also a climber, moving easily through trees. Her feet were particularly intriguing. Unlike modern humans, her big toe was opposable, more like a thumb, allowing her to grasp branches. Yet the structure of her midfoot showed adaptations for walking flat on the ground, something no living ape combines in the same way. The discovery rewrote assumptions about what the earliest human ancestors looked like. For decades, many scientists had imagined our lineage evolving from chimpanzee-like creatures that gradually became more human. But Ardi suggested that both humans and chimps descended from something different, an older ancestor that was neither knuckle-walking nor fully terrestrial. In Ardi's world, upright posture did not begin in open savannas, but within forested habitats, where flexibility mattered more than specialization. Her skull and teeth added more clues. Ardi's face was less protruding than that of modern apes, with smaller canines that lacked the sharp, weapon-like form used by male chimpanzees in dominance displays. The reduction of canine size in both males and females hinted at a profound behavioural shift. Less aggression, more social stability, perhaps even the beginnings of pair bonding. In a species where competition for mates softens, cooperation and parental care become more advantageous. Some researchers proposed that these social changes may have been among the earlier steps toward what would later define our lineage. Not just walking, but bonding. Reconstructing Ardi's world required more than bones. The sediment and fossil plants found alongside her told a story of environment. 4.5 million years ago, the Middle Awash region was not desert, but a mosaic of woodlands, with rivers lined by trees and open patches between them. The climate was mild, seasonal, and diverse, home to monkeys, antelopes, elephants, and ancient birds. Ardi's species likely foraged for fruits, roots, and leaves, both on the ground and in the canopy, sleeping in trees for safety but walking on 2 legs when travelling short distances. This woodland context challenged the long-held savanna hypothesis, which had argued that bipedalism evolved when our ancestors left the trees to adapt to open grasslands. Instead, Ardi showed that upright walking may have developed long before the savanna spread. It might have been an advantage not of distance, but of dexterity, freeing the hands for carrying food, infants, or even social gifts. In her forest home, walking upright was not about migration or conquest, but balance and survival in a complex environment. The reconstruction of Ardi's skeleton took nearly 2 decades, involving hundreds of scientists and specialists in anatomy, geology, an isotopic analysis. When the results were finally published in the journal Science in 2009, they caused a sensation. Ardi was described as a mosaic of evolution, bridging the gap between ancient apes and the earliest members of our lineage. Her anatomy revealed that the last common ancestor of humans and chimpanzees was likely not chimp-like at all. Instead of a knuckle-walking, aggressive animal, the ancestor may have resembled Ardi, a careful climber, partly bipedal, with a relatively peaceful social structure. Of course, not everyone agreed. Some researchers questioned the interpretation of her pelvis and foot, arguing that the evidence for habitual bipedality was overstated. Others cautioned that behavioural inferences, like reduced aggression or pair bonding, should be treated carefully, as they are impossible to test directly in fossils. Yet even among critics there was little doubt that Ardipithecus ramidus had changed the framework of discussion. She showed that evolution was not linear or predictable. It branched and twisted, exploring many forms before settling on ours. To imagine Ardi alive is to see a creature at ease in two worlds. Picture her moving through a sun-dappled woodland, her long fingers curling around a branch, her feet gripping bark with delicate precision. She pauses, lowers herself to the ground and walks a few steps upright, her spine steady, her balance cautious but confident. Nearby, others in her group move quietly through the understory, grooming, foraging, perhaps carrying infants. The air hums with insects and the calls of birds. Predators lurk beyond the trees, but Ardi's group is alert and cohesive, relying on vigilance rather than violence. In this vision, the roots of humanity appear not in aggression or conquest, but in cooperation and adaptability. Ardi's anatomy reminds us that the earlier steps toward being human may have had more to do with restraint than with dominance. Smaller canines mean fewer fights. A flexible hand means sharing and grasping. An upright posture means new ways to interact, to reach, to carry. These subtle shifts, accumulating over millions of years, would shape not only our bodies but our societies. Ardi's discovery also reshaped our sense of humility in the story of evolution. For much of the 20th century, it was easy to imagine humans as the end goal of a long straight ascent from primitive ancestors. But fossils like Ardi tell a different story, one of variation, adaptation, and chance. She was not a missing link, nor a perfect prototype, but one of many forms exploring what was possible. Evolution is less a ladder than a forest itself, full of branches that grow, split, and fade. And somewhere among those branches, Ardi's line continued for a while, long enough to pass on certain habits of body and behaviour that would echo through later species. Her way of walking, her social calm, her dual life between ground and tree, all of it would become part of a deeper rhythm in the human story. Not a march toward progress, but a slow, experimental drift guided by survival and circumstance. Standing in front of Ardi's reconstructed skeleton today, her delicate pelvis, her opposable toes, her small, thoughtful skull, it is hard not to feel a sense of closeness. She lived millions of years before us, yet her bones tell of balance, cooperation, and care. Qualities that, for all our technology and ambition, remain the truest measures of what it means to be human. And as always in this field, we end not with certainty but with wonder. Ardi may or may not be our direct ancestor. We may never know if she looked up at the same stars we do, or if her species quietly vanished, leaving no descendants at all. But her fossils whisper something profound, that our roots run deep, tangled through forests long vanished, and that the path to becoming human was not a straight road, but a winding climb through the trees. What if evolution was less a family tree, and more a crowded forest? Between 4 and 2 million years ago, Africa was not the stage for a single lineage slowly transforming into us, but a continent alive with many kinds of humans, not in name, but in form, in posture, in the quiet rhythms of their days. For much of the 20th century, textbooks and museums presented human origins as a simple sequence: ape-like ancestors giving rise to upright hominins, then toolmakers, then finally Homo sapiens. But the fossil record tells another story. It is not a line, nor even a tree, but something closer to a dense woodland of branching lives, where multiple species evolved, coexisted, and vanished, often sharing the same environments and even the same instincts for survival. By about 4 million years ago, the forests of East Africa were shrinking. Cycles of wet and dry climates had begun reshaping the landscape into open woodlands and savannas. This environmental instability did not create a single evolutionary response. It produced many. Some species clung to trees and mixed diets, others adapted to more open habitats, and still others experimented with walking fully upright. The result was a burst of diversity, a radiation of hominins across the continent. Each species represented a slightly different solution to the same problem: how to live between the forest and plain. In the region that is now Ethiopia, the descendants of earlier species like Ardipithecus gave rise to forms we recognise as Australopithecus. These were small-bodied, big-jawed beings, with long arms for climbing, but hips and knees built for bipedal walking. The most famous among them, found decades later in the Awash Valley, would be called Lucy, but she was just one among many. Around the same time, in Kenya's Turkana Basin and Tanzania's Olduvai region, other australopiths evolved their own adaptations, some robust with heavy chewing muscles and massive molars, others more graceful, slender, and mobile. Fossils from the period reveal an astonishing range of forms. Some skulls are delicate, with rounded crania and smaller teeth, others are wide-faced with jaws like vices, designed to crush tough vegetation. Some pelvic bones show efficient striding on open ground, others hint at continued comfort in trees. Even within a single site, variation blurs the boundaries between species. It is as if evolution itself was uncertain, testing multiple prototypes at once. The pattern suggests that hominins were not marching toward a goal, but branching into parallel experiments, some of which flourished for millions of years before fading quietly away. This diversity was first hard for scientists to accept. For decades, paleoanthropology sought the ancestor, the one true link leading directly to modern humans. Each new fossil discovery was hailed as the missing chapter, the next rung on the ladder. But by the mid-20th century, the evidence refused to fit that simplicity. In places like Hadar, Laetoli and Sterkfontein, fossils of different body types and morphologies appeared in the same layers of time. Rather than one evolving species, there were several, overlapping and sometimes contemporaneous. Take the example of East Africa around 3 million years ago. There, Australopithecus afarensis, the species of Lucy, walked upright across the volcanic plains, leaving footprints in the soft ash that would one day harden into the famous Laetoli tracks. But at roughly the same time, in what is now Kenya, another species called Australopithecus anamensis still showed older traits, with stronger forearms and a slightly more ape-like skull. Meanwhile, to the south, other australopiths evolved heavier jaws, culminating in what scientists later called the robust lineages, forms like Paranthropus boisei and Paranthropus robustus. These cousins, sometimes nicknamed nutcrackers, developed skulls reinforced like architecture, able to withstand immense chewing forces. They likely fed on tough roots and fibrous plants in dry seasons when softer foods were scarce. And yet, none of these species can be called primitive. Each was exquisitely adapted to its own ecological niche. Evolution, after all, does not reward progress. It rewards persistence. Some australopiths may have spent much of their time on the ground, others in trees. Some lived near lakes and rivers, others on open plains. The fossil record shows that for millions of years, these forms coexisted in complex overlapping patterns. There was no single moment when one became human. Instead, there was a long braided process of adaptation and extinction, as different lineages tried different ways of being. Their environments were anything but stable. Across the African continent, tectonic activity was reshaping the Rift Valley, altering rainfall and vegetation patterns. Massive lakes would form, then dry up. Forests would advance, then retreat. Every few 100,000 years the conditions changed, favouring different diets, different locomotions, and different behaviours. These cycles acted like a rhythm of trial and error written into bone. For a species to survive here, it needed flexibility, not perfection. And that perhaps is what defines this era. Not the emergence of modern traits, but the diversification of possibilities. If one could walk through Africa during those 2 million years, the variety of hominins would be remarkable. In one valley, a small group of Australopiths might be cracking nuts with pebble tools. In another, heavier cousins would be digging roots with powerful hands. Some groups would move in loose bands, carrying infants, gathering fruits and watching for predators. Others would cling to forest margins, foraging in safety among trees. All of them would share certain features: upright posture, dexterous hands, complex social awareness, but none would yet possess the defining hallmarks of humanity. Theirs was an age of potential, not destiny. For researchers today, this diversity complicates the search for ancestry. Fossils rarely preserve in clear, unbroken lines. Instead, they appear as scattered pages of a book half-burned by time. Some pages overlap, others contradict. Even the species' boundaries are debated. Where one ends and another begins may depend on which bones you emphasize. Are the robust Australopiths offshoots of the same lineage, or separate experiments that evolved parallel traits? Was Australopithecus afarensis the ancestor of all later humans, or merely one of several branches leading nowhere? The evidence allows for multiple interpretations, and that uncertainty is part of the story itself. What we can say, as far as the fossils whisper, is that Africa around this time was teeming with evolutionary creativity. The Rift Valley acted as both cradle and crucible, a corridor of change where isolation and movement intertwined. Populations split and rejoined, adapted and vanished, leaving behind clues in sediments and teeth. To trace that record is to watch evolution behaving like weather, fluid, responsive, and unpredictable. And yet, amid all this variation, certain patterns began to emerge. Over time, a few lineages started to show subtler changes in proportion: slightly longer legs, narrower hips, smaller teeth, and hands capable of greater precision. These were not leaps forward, but quiet adjustments to new ways of living. They suggest shifts in diet and movement, in the balance between strength and endurance. By around 2.5 million years ago, one of these experiments would give rise to a new genus entirely: Homo, whose members would begin to shape their world with tools. But even then, the older forms persisted, living alongside their tool-making cousins for hundreds of thousands of years. So when we speak of human evolution, we should imagine not a parade of ancestors marching in single file, but a landscape full of lives, species overlapping in time, competing and coexisting, each a version of the same idea: survival through adaptation. The family tree of humanity is less like a diagram and more like a living forest, dense with growth, its roots intertwined, its branches reaching in all directions. Some branches ended abruptly, others bent toward the light and continued, but all shared the same soil, the same ancient ground from which every step we take still rises. This crowded evolutionary forest reminds us that being human was never inevitable. It was the outcome of chance, variation, and resilience, a pattern of emergence rather than progress. The fossils of this era, broken jaws, scattered teeth, fragments of pelvis, do not tell a story of straight ascent. They tell of complexity, of experimentation, of a lineage that could have turned out many different ways. In that sense, the story of 4 to 2 million years ago is less about who we were and more about who we could have been. If evolution had favoured different adaptations, another branch might have survived instead. Perhaps a more robust species, better suited to harsh seasons, would have inherited the Earth. Or perhaps none would have endured, and the planet would be left without the peculiar consciousness that now looks back and wonders. But what actually happened, what carried one branch forward while others disappeared, was not intelligence or even strength, but flexibility, the ability to live through change, to move across landscapes both physical and ecological. That trait, subtle and unglamorous, may have been the true inheritance from this time, the capacity to adapt without knowing what comes next. So when we look back across the fossils of those millions of years, we are not seeing a missing link or a single origin point. We are seeing a field of possibilities, a chorus of early lives that together compose the first movement of our story. And in their diversity lies the most human lesson of all, that nature's path is rarely straight, and our own existence is just one of many ways it could have turned out. Could interbreeding, not replacement, be the real engine of progress? For much of the last century, scientists pictured human evolution as a clear and orderly branching tree, each species dividing, spreading, and eventually being replaced by something newer, smarter, and more efficient. It was a comforting image, a tidy diagram of progress leading somehow inevitably to us. But what the fossils and later the genes began to reveal was not a clean succession, but a messy family reunion. Species overlapping in time, exchanging not only tools and behaviours but also genes. What once looked like replacement may have been conversation, a long, tangled dialogue written into DNA. By 1 million years ago, the world was already crowded with different kinds of humans. There were tall, long-limbed Homo erectus populations stretching from Africa to Java and China, shorter and sturdier forms adapting to new climates, and perhaps others that we have only begun to glimpse through fragments of bone and genetic echoes. The Earth itself was unstable, pulsing between glacial and interglacial cycles. Environments shifted, and populations migrated with them, sometimes splitting apart, sometimes rejoining. In those shifting zones of contact, coastal corridors, mountain passes, fertile valleys, something quietly revolutionary happened. Populations that had been separate for hundreds of thousands of years began to meet again, and some of them mated. For a long time, this idea was resisted. The traditional replacement model of human evolution, often called out of Africa, assumed that modern humans evolved in isolation and then spread across the planet, displacing older forms without mixing. It was a model built on purity and succession, not connection. But in the 21st century, ancient DNA cracked that illusion open. When geneticists sequenced the first Neanderthal genome, they found something shocking. Traces of Neanderthal DNA inside the genomes of living humans outside Africa. The implication was unmistakable. Our ancestors had not simply replaced the Neanderthals, they had met them, lived with them, and had children with them. The same revelation came from another ghost population, discovered not through fossils but through genetics. In a Siberian cave known as Denisova, a single finger bone yielded DNA so distinct it belonged to an unknown lineage, neither modern human nor Neanderthal, but something in between. Denisovans, as they were later called, left genetic traces in people from East Asia, Oceania, and parts of the Americas. Their DNA includes adaptations for high-altitude living that survive in Tibetan populations today. This means that the inheritance from those encounters is not just a memory. It is part of how some of us live and breathe right now. Even before the DNA confirmed it, the fossils had hinted at these crossings. A jawbone found in Romania, dating to roughly 40,000 years ago, carries anatomical features between Neanderthals and modern humans. Later genetic work showed that its owner had a Neanderthal ancestor just a few generations back. Other finds, such as hybrid skulls from Central Asia, and possible mixture signatures in fossils from Israel and Siberia, add to the picture. These were not rare or isolated events. They were part of the normal flow of contact whenever populations met after long separations. The realization changed everything about how scientists understood evolution. Instead of a branching tree where each limb grows in isolation, the new image became what some call a braided stream. In this model, lineages diverge like rivers, wander across landscapes and occasionally rejoin, mixing their waters before flowing apart again. It is a vision of evolution as fluid and interconnected, a network rather than a hierarchy. In the case of our genus, Homo, it suggests that genetic exchange, not replacement, was one of the main forces shaping our species. What makes this idea so profound is that it reframes progress itself. The rise of modern humans was not the triumph of one superior lineage, but the outcome of diversity, interaction, and blending. Each encounter left traces that were tested by time. Some genes survived because they offered advantages, resistance to diseases, better adaptation to climate, or improved metabolism. Others faded away. The result was a mosaic genome, a biological memory of contact zones stretching across continents and millennia. One of the clearest examples of this blending is in our immune system. Some of the genetic variants we inherited from Neanderthals influence how we respond to pathogens today. Others, passed from Denisovans, help regulate oxygen levels at high altitudes. In a sense, hybridization acted as a shortcut to adaptation, allowing populations to borrow ready-made solutions from others who had already faced similar challenges. It was not an accident or anomaly. It was part of how evolution innovated. Fossil evidence continues to reveal how close these encounters might have been. In caves across Europe and Western Asia, Neanderthals and early modern humans occupied the same regions, sometimes alternating layers of habitation in the same shelters. Stone tools and hearths appear side by side, and where patterns on teeth suggest similar diets. It is not hard to imagine moments of meeting, shared hunts, exchanged gestures, or even curiosity across the boundaries of difference. We will never know what those encounters looked like, but we carry their results in every cell of our bodies. The discovery of hybridization also exposed how deeply the idea of the missing link had misled us. For centuries, scientists searched for a single fossil that could explain the transition between species, as if evolution moved in straight lines, one form giving birth neatly to the next. But the genetic record shows a different pattern, species diverging and reconnecting, evolving together rather than apart. The gaps between them were not missing links but zones of contact, places where the boundaries blurred. This understanding reaches far beyond human evolution. Hybridization is common throughout nature. Birds, fish, and mammals all exchange genes when populations overlap. It introduces variation, speeds adaptation, and can even give rise to new species. What makes humans unique is not that we interbred, but that we can now read that story in our DNA. The braided stream model simply brings us back into the larger logic of life itself, evolution as a network of connections rather than a ladder of ascent. Yet for all this, the picture remains incomplete. DNA does not survive everywhere, and the fossil record is still fragmentary. We know about Neanderthals and Denisovans because conditions preserved their bones, but there may have been other populations, ghost lineages, whose genetic threads run through us unseen. Some genetic studies suggest that as modern humans left Africa, they encountered at least one additional archaic group in Asia, contributing DNA that cannot yet be traced to any known fossils. These lost relatives may never be identified, but their legacy endures quietly within us. The discovery that we are hybrids of hybrids also changes how we think about identity. It reminds us that species in the human story has never been a fixed boundary, but a shifting threshold. Our ancestors were not pure types, but participants in an ongoing exchange of traits and ideas. In this sense, humanity was not born in one place or moment. It was assembled, piece by piece, through contact and recombination. Each meeting across time added another layer to what we now call us. This view can be unsettling because it dissolves old hierarchies. The line between us and them, between modern and archaic, becomes harder to defend when the evidence shows that those others live on in us. But it is also a profoundly humbling realization. The genetic echoes of Neanderthals, Denisovans, and other forgotten populations remind us that survival is not a story of isolation, but of entanglement. We are not the end of evolution's chain. We are one of its knots, and perhaps that is the real engine of progress, if progress can even be the right word. Not replacement, but exchange. Not competition, but continuity. In the slow tides of time, species rise and fall, but the information they carry, the genetic innovations, the learned behaviours, flow onward. The braided stream keeps moving, reshaping itself as it goes. Every discovery of interbreeding reminds us that life does not advance by erasing its past, but by folding it in, again and again. So when we imagine the story of our origins, we should not picture a single line reaching upward, nor even a branching tree. We should picture the surface of a river delta at dusk, channels diverging and reconnecting, their waters mingling in complex luminous patterns. Somewhere within that shifting network, between 1,000,000 and 40,000 years ago, our ancestors met others who were both different and familiar. They spoke in gestures, exchanged genes, and disappeared into time, leaving us as their living synthesis. And in the quiet recognition of that truth lies a deeper understanding of what it means to be human, not a species apart, but a collection of borrowed fragments carried forward by the current of life. If evolution is a river, how many times did our channels merge again? For generations, scientists tried to draw the story of life as a line, as if each species passed the torch neatly to the next, the past vanishing as progress advanced. Later, the line became a tree, branching and diverging through time. But the deeper we looked, into fossils, into genes, into the invisible threads that connect living things, the less tidy that tree became. Branches that once seemed separate curved back toward each other, crossing and reconnecting. Some vanished beneath the surface, only to reappear downstream in new forms. It was not a tree at all. It was a river system, a braided stream where evolution flows forward through time, endlessly splitting and rejoining, reshaping its own path. The idea of the braided stream emerged gradually, as researchers struggled to describe the complexity that genetic evidence revealed. The old diagrams could not hold the truth anymore. They were too clean, too simple, too comforting. The fossil record had already hinted that species did not replace one another in perfect sequence, but overlapped, coexisted, and even shared traits. Then DNA made the metaphor undeniable. Our genomes turned out to be palimpsests, layers of inheritance written and rewritten by contact, migration, and adaptation. The boundaries between species, once thought sharp and permanent, proved porous. Genes flowed across them like water seeping through sand. To understand this, it helps to imagine evolution not as a ladder, nor as a map of descent, but as a dynamic system of exchange. Populations are like channels within a river delta. Each has its own course, sometimes running parallel, sometimes crossing, sometimes merging. A drought or flood, a change in climate, geography, or behaviour can alter the flow, redirecting the currents of inheritance. Over time, some channels dry up, others deepen, carrying the collective legacy of those that came before. In this view, there is no single direction of progress, only movement, continuity, and change. The power of the braided stream model lies in its honesty. It accepts what both fossils and genes insist upon, that life evolves through connection as much as through separation. The traditional tree model emphasizes divergence, species splitting apart from common ancestors and becoming distinct. But divergence is only half the story. The other half is convergence, the tendency for separated lineages to meet again, to exchange genes or behaviours before parting once more. This oscillation between splitting and merging, between isolation and reconnection, drives much of evolutionary innovation. It introduces variation faster than mutation alone ever could. In humans, this process has been exceptionally intricate. Our ancestors did not march across prehistory like a conquering lineage. They spread in waves, encountered others, and exchanged not only tools but bloodlines. Gene flow from Neanderthals and Denisovans is the best-known example, but it likely happened many times before and after. Each episode added new combinations of traits, reshaping physiology, immunity, and adaptation. When seen through this lens, humanity's evolution becomes less like a story of survival of the fittest, and more like a record of survival through sharing. The same logic applies across the tree of life. Hybridization is now known to play a key role in the evolution of birds, fish, and even plants. It is a creative force, blurring boundaries and allowing useful adaptations to move between species. The genetic exchange that once seemed messy or anomalous is, in fact, the mechanism by which ecosystems remain dynamic. In evolutionary terms, purity is fragile, mixture is strength. The braided stream captures that truth far better than any static lineage chart ever could. In this framework, introgression, the technical term for gene flow between distinct populations, acts like a feedback loop. Imagine two species separated by geography or behaviour for thousands of generations. Each adapts to its own environment, accumulating unique mutations. When environmental shifts or migration bring them back into contact, those mutations can mingle. Some combinations fail, others thrive, spreading rapidly if they improve survival. The outcome is not a simple blend, but a new equilibrium, a reshaped population carrying the evolutionary experiments of both parents. Over millions of years, these pulses of introgression act as the tuning mechanism of life. Scientists have even begun to model these feedback loops mathematically, tracing how genes rise and fall through time like ripples on water. The patterns reveal something humbling. Evolution is not a march from simplicity to complexity, nor from weakness to strength. It is a continuous circulation of possibilities. What looks like innovation often comes from recombination. the reassembly of existing parts in new ways. The braided stream expresses this elegantly. It tells us that change does not come from a single source, but from the endless movement of ideas, biological, ecological and behavioural, through the current of time. This model also reshapes how we think about extinction. In the ladder view, extinction is final, a broken link, a lost rung. In the tree model, it is the pruning of a branch, but in the braided stream, extinction is less absolute. The species may disappear, but its genes may continue downstream, woven into others. In this sense, nothing vanishes completely. Every genome carries the ghosts of those that came before, fragments of vanished populations folded into new forms. The living world is thus a palimpsest of survival, a record of presence without permanence. Even our culture reflects this same pattern. Ideas, technologies and languages do not evolve linearly. They branch, merge, and recombine across time. Words migrate between tongues, inventions reappear in new contexts, myths echo across continents. The logic of the braided stream extends beyond biology. It describes the evolution of thought itself. Knowledge flows like water, sometimes clear, sometimes muddied, but always moving forward through exchange. The beauty of the model lies not only in its complexity, but in its humility. It rejects the notion of a central species, a privileged lineage, or a chosen path. Instead, it invites us to see evolution as a vast community of interactions. Every form of life contributes to the whole, shaping and reshaping the flow in ways no single lineage could predict. The braided stream is democratic in the truest sense. No one current defines the river, and yet the river exists because of all of them together. It also reminds us that our own story is unfinished. Just as our ancestors once met and mingled with other kinds of humans, we continue to shape the evolutionary flow, though now at unprecedented speed. Our movements, technologies, and choices alter the distribution of genes, the survival of species, and even the climate itself. We have become, in a sense, caretakers of the river, but the river remains beyond our control. It moves with its own logic, slower and deeper than any civilization can measure. The braided stream also challenges the way we visualize time. In most narratives, the past lies behind us, fixed and unreachable. But evolution does not flow in straight chronological order. Genes can resurrect traits from ancient ancestors, reintroduce lost adaptations, or blend archaic elements into new forms. The past is not gone. It is folded within the present, alive in every molecule of DNA. The river of evolution flows not only forward but inward, circulating its memory. When this idea first entered scientific thinking, it met resistance. Simplicity is seductive, and the old diagrams were comforting in their order. But the evidence left no choice. Every genome sequenced, every fossil reanalyzed, revealed a world more intricate than the linear or branching models could explain. What emerged was not chaos, but pattern, an elegant complexity that reflected the living world's resilience. The braided stream became not just a metaphor, but a framework for understanding how life endures change. If one could step back and see Earth's history from above, the planet itself might look like a vast delta, rivers of evolution fanning out, crossing and merging over billions of years. From the first cells to the first apes to us, the same principle holds. Connection is creation. Isolation breeds fragility. Flow breeds life. Every gene that survives has passed through countless mergers and splits shaped by both chance and necessity, and perhaps this is the quiet lesson the braided stream leaves us with, that progress is an illusion, but persistence is real. The current does not move toward perfection, only continuity. Species rise, mingle and vanish, but the flow endures. To exist at all is to be part of that motion, to be carried by forces older than thought, older than language, older than the idea of evolution itself. The braided stream is not only a scientific model, it is a metaphor for humility. It tells us that nothing, not even extinction, is truly separate. Every living thing is connected to every other by the slow, patient water of time. We are each a temporary eddy in that current, swirling for a moment before merging back into the flow. The river continues, unbothered by our attempts to map it, its course written not in certainty, but in movement. Why do we need a single fossil to feel complete? It seems like an odd thing to crave. A bone, a skull, a fragment of a jaw. Yet for more than a century the phrase "the missing link" has had a strange pull on the human mind. It is not just a scientific idea, but a psychological one. It promises closure, a neat line between what we were and what we became. It offers the illusion that somewhere out there is a single relic that explains everything. The moment ape became man, ignorance became reason, darkness became light. That desire is older than science itself. It is the story of every myth where something once whole is lost and must be found again. The irony, of course, is that evolution never worked that way. There was never one creature that woke up halfway between species, wondering what it was. The link exists only in our imagination, a placeholder for our discomfort with continuity, our impatience with gradual change. The fossil record, with its millions of years of overlap and subtle transitions, doesn't fit our taste for drama. We want a single turning point, not a slow rearrangement of forms. And so, in the public mind, science became a treasure hunt for an idol that never existed. The 19th century had already primed the world for this myth. Industrialization, empire, and Darwin's new vision of natural history collided in an age hungry for progress narratives. People saw the universe itself as a staircase, ascending from primitive matter to human mind. When Darwin suggested that humans were part of that same continuum, the idea was shocking but strangely seductive. If evolution was a ladder, then there had to be a rung that connected us directly to the apes, a missing step that proved the story true. The public demanded that science find it. The phrase "missing link" became shorthand for that proof, simple enough for newspapers and Sunday sermons alike. When newspapers in London or New York printed stories of new fossils, they were not reporting slow, careful science. They were selling revelation. Each new discovery was heralded as the long-sought link, as though scientists had unearthed the holy grail of humanity. It didn't matter that researchers themselves often avoided the term. Once it entered the press, it became gospel. Headlines spoke of Ape-Men, first humans, and the dawn ancestor. The public imagination turned messy evolution into a single moment of transformation, a cinematic scene where one creature takes a step into history and becomes us. That longing for a defining fossil says more about us than about evolution. It reflects our need for identity through contrast. To know who we are, we invent a before and an after, a line that separates humans from everything else. But nature does not draw such lines. Every fossil that once seemed a missing link eventually becomes another branch, another experiment in being alive. We keep redrawing the map, but the lines never stay still. The legacy of Piltdown amplified this cultural illusion. For 40 years, that forged skull reassured Europe that the cradle of humanity was close to home. It confirmed what people already wanted to believe, that civilization, intellect, and whiteness had ancient roots in the soil of England. It was a fossil tailored to prejudice, not to truth. When the fraud was finally exposed in the mid-20th century, it left a deeper scar than just scientific embarrassment. It showed how easily evidence can be shaped by expectation, and how science, when filtered through pride, can turn into mythology. Piltdown Man was a lie, but it succeeded because it told people what they needed to hear. That pattern persists in quieter forms today. Every few years, a new fossil is hailed online or in headlines as the missing link, between fish and land animals, between apes and humans, between anything and anything else. The irony is that scientists are usually the first to avoid the phrase, but journalists know its power. Missing link is cinematic, digestible, and gives readers the satisfaction of discovery without complexity. The actual science about mosaic anatomy, shared traits, and evolutionary branching rarely fits into a headline. Complexity does not go viral. Certainty does. Our language itself traps us. The word link implies a chain, something linear and complete, something that can be broken or repaired. But evolution is not a chain. It is more like a web, or as we have learned, a braided stream. Nothing is missing, only our understanding is incomplete. Yet we keep using the language of loss and recovery. We talk about finding origins, discovering beginnings, as though humanity were a story with a single opening chapter. In truth, our beginning is a spectrum of experiments in being human, overlapping through time, none aware of where it would lead. Philosophically, this obsession also reveals our discomfort with ambiguity. We crave sharp boundaries, animal and human, primitive and modern, past and present. The missing link myth comforts us by promising that the boundary is real and that we have crossed it. It tells us that there was once a moment of arrival when intelligence, morality, or soul appeared fully formed. But nature, as it turns out, prefers gradients. Evolution blurs, not divides. Every threshold we think we've found dissolves under closer study. The media, of course, amplifies this yearning because it mirrors how we think about ourselves. The missing link is not only about prehistory, it's about identity. We want to know what makes us special, what separates us from the rest of life. If we can find that one fossil that stands halfway between ape and human, we can point to it and say, that's where the difference began. But difference is a process, not a point. The line we search for is not in the ground, it's in our minds. Even our films and fiction borrow the same template. The image of the half-evolved being, the noble savage, the Ape-Man, the primitive ancestor, haunts popular culture. It appears in everything from early pulp novels to modern documentaries, always as a mirror of human insecurity. The figure of the missing link becomes a symbol of transformation, but also of anxiety. It reminds us that we too are animals trying to justify our minds. The irony is that the more we learn, the less we fit into the simple categories our ancestors built. The genetic and fossil record now show that humanity was never a single thread but a tapestry. We are not descended from one species, but from many, all contributing to what we are. Yet the public conversation still prefers a single ancestor, a single origin point, because simplicity feels safer than truth. This is not just a problem of communication, it is a reflection of how science and storytelling intertwine. Humans understand through narrative. We need beginnings, middles, and ends. Evolution, on the other hand, has none of those. It is continuous, recursive, and endless. To translate it into stories, we invent symbols, the missing link being one of the most powerful. It compresses millions of years of complexity into a single satisfying image, the bridge between what was and what is. But every bridge we build across that abyss eventually collapses under the weight of new data. Still, the metaphor persists because it serves an emotional function. It lets us imagine that we are not accidents, that there was purpose in the path that led to us. The missing link becomes a stand-in for destiny, a fossilized moment of becoming. It reassures us that our existence was inevitable, that evolution was somehow aimed in our direction. But biology tells a humbler story, one of branching possibilities, of chance encounters and narrow survivals. If there is a lesson in our lineage, it is not that we were destined to appear, but that life, given enough time, will fill every possible niche, including one that thinks about itself. Language shapes science as much as evidence does. When we call something a link, we imply completion. When we call it an ancestor, we imply hierarchy. When we call it primitive, we imply value. Words sneak in bias. That is why many modern scientists now prefer to speak of transitional forms, shared ancestors, or evolutionary cousins. The shift may seem semantic, but it matters. It changes how we see our place in the story, not at the top of a ladder, but among countless branches that still live alongside us. Perhaps the most profound realization is that we are the ones missing something, not evolution. We are missing comfort with uncertainty, patience with slowness, reverence for continuity. We have been trained by centuries of progress narratives to think that everything must lead somewhere, that every discovery must close a gap. But in truth, the beauty of science lies in its open ends. Every answer reveals deeper questions. Every fossil expands the mystery instead of resolving it. And so, the missing link we invented remains unfound because it was never real. It was a metaphor mistaken for evidence, a mirror mistaken for a window. What we were really looking for was reassurance that the story of life made sense, that it led to us in a straight line. But evolution does not tell stories. We do. And the more we learn about our tangled ancestry, the more it humbles us. There was never a single moment when humanity began, only an unbroken chain of creatures adapting to survive one footstep at a time. In the end, perhaps the missing link is not buried in the earth, but embedded in our need to draw lines where none exist. We invented it to make peace with our own origins, to give shape to a past too vast to comprehend. And though the myth is false, the longing behind it is deeply human. We want to understand how something as fragile as consciousness could have emerged from nature. But maybe that is the wrong question. Maybe the truth is that consciousness was never separate from nature. It was nature learning to look back at itself. What if evolution sometimes goes backwards, or lies to us entirely? It sounds absurd for a process built on adaptation and progress, but in truth, nature has no sense of direction. It doesn't build toward perfection, or even toward us. Evolution is not a story written by an author. It is an ongoing improvisation where every organism tries, fails, and tries again under the pressure of change. In that chaos, some species move forward, others retreat, and some perform evolutionary pranks so strange they almost seem like jokes. Snakes that try to grow legs again, whales that abandon the land, and insects that reinvent flight long after losing it. These reversals are not mistakes. They are reminders that life doesn't march, it meanders. For most of history, people assumed evolution was a one-way climb, an ascent from simple to complex. But when biologists began to look closer at the genetic and fossil record, they found a different kind of narrative. Evolution can and does reverse itself, often spectacularly. Some species regain lost traits, others converge on the same solution from entirely different starting points. The result is a world filled with lookalikes that share no direct ancestry, and throwbacks that revive ancient forms for modern needs. In such a world, the idea of a neat missing link becomes not just wrong, but impossible. There is no straight path to trace, only a web of overlapping experiments. Take the whales. Around 50 million years ago, their ancestors were small, four-legged land mammals, not so different from deer. These animals, called artiodactyls, lived near ancient coastlines, browsing for food. Over generations, some began spending more time in the water, finding safety and abundance there. Their limbs adapted to paddling, their nostrils crept upward, their bodies streamlined. Within a few million years, they had done something extraordinary. They reversed the great exodus of life from the sea. Where fish had once crawled onto land, their descendants now slid back into the water. The story of whales is not evolution's triumph. It is its perfect joke. They became air-breathing creatures that cannot live on land, descendants of landwalkers who traded feet for fins. Even now, whales carry small vestiges of their terrestrial past. Tiny internal leg bones, ghost limbs hidden in their flesh like whispers of the creatures they once were. And they are not alone. Snakes, which long ago lost their limbs as they evolved to slither through soil and undergrowth, sometimes attempt to grow them back. Pythons and boas possess tiny remnants of hind legs, minute spurs buried beneath their scales, complete with vestigial pelvic bones. These structures serve no purpose today, yet they persist as genetic echoes, showing that evolution is not clean or final. Once a gene exists, it can linger, mutate, or reawaken given the right trigger. The same mechanism allows fish living in perpetual darkness to regain their sight when light returns, and lizards on isolated islands to re-evolve lost traits like limbs or armour when the environment changes again. This process, known as reverse evolution or evolutionary reversal, is nature's way of recycling. DNA is not a sculptor's chisel that only carves forward. It is more like clay, endlessly reshaped by circumstance. When conditions shift, old blueprints can be reactivated. A lineage may appear to have reversed course, but in reality, it is adapting to a familiar challenge using dormant tools. To an observer, this can look like time running backward, but it's really time looping. Then there's convergent evolution, which is perhaps evolution's most convincing illusion. Here, unrelated species evolve to look and function almost identically, despite having entirely different ancestries. The classic example is the uncanny resemblance between dolphins and ichthyosaurs. Dolphins, as we know, are mammals, warm-blooded, air-breathing descendants of land animals. Ichthyosaurs, on the other hand, were reptiles, closer to lizards than to whales, yet both developed streamlined bodies, dorsal fins and flippers, perfect solutions to the physics of moving through water. They even evolved similar tail shapes and eye placements. To a casual observer, they could be mistaken for the same animal, separated only by 100 million years. Evolution repeated itself because physics demanded it. This pattern happened everywhere. In Australia, marsupial mammals, like the Tasmanian tiger or the sugar glider, evolved in isolation but ended up looking strikingly like placental mammals in other parts of the world. The Tasmanian tiger mirrored wolves, the sugar glider mirrored flying squirrels. None of them were related, yet their environment sculpted them into near-identical forms. Nature doesn't care about ancestry, it cares about what works. When the same problem arises in two different places, evolution often solves it in the same way. That is why scientists often call convergent evolution nature's déjà vu. It tricks us into thinking we found a missing link or a direct descendant, when in fact we're looking at coincidence, not continuity. Similarity does not always mean connection. Wings evolved at least 4 separate times, in insects, birds, bats and pterosaurs, each from a different origin point. The ability to fly is not evidence of a shared ancestor. It is evidence that flight is a good idea. Evolution reuses ideas endlessly, as if nature has limited patience for originality. Sometimes it even goes in circles. Consider the stickleback fish. After the last ice age, some populations became trapped in isolated freshwater lakes. Over time, they adapted to the new environment, losing their heavy armor plating and developing new body shapes. But when the glaciers melted and saltwater returned, some of those freshwater populations found themselves re-entering the sea. Within a few thousand years, they had re-evolved the same armor plates their ancestors once had. To a paleontologist looking only at fossils, it might appear as if one species had never changed at all. In reality, evolution had simply retraced its own steps. These reversals and repetitions highlight a fundamental truth. Evolution is opportunistic, not directional. It does not strive for complexity or progress. A trait that disappears can return. A structure that evolves can vanish. The environment is the sculptor, not the plan. When climate, competition or geography shifts, the same pressures can reawaken ancient potentials. Evolution is less like a ladder climbing toward perfection, and more like a landscape shaped by wind, forever changing, yet never finished. In some ways, the fossil record itself can be misleading. When we find transitional species, those that share traits of two different groups, we are tempted to see them as steps on a linear path. But in light of convergent and reverse evolution, those fossils may instead represent side experiments or repeated solutions. What looks like a missing link might simply be another instance of nature rediscovering a good idea. Even extinction doesn't always end a story. Traits that vanish in one lineage can reappear in another through convergence. Birds, for example, lost their teeth over 100 million years ago. Yet certain lineages of fish and reptiles independently evolved beak-like structures that mimic the same function, proof that evolution never truly discards a successful design. Genes can remain dormant for eons, waiting for conditions that make them useful again. It's not that evolution forgets, it just pauses. Reverse evolution also challenges one of our deepest assumptions, that once complexity arises, it can't go back. But simplicity too can be an adaptation. Parasitic organisms like tapeworms and fungi have shed organs, systems, even entire body plans in exchange for efficiency. Some bacteria have lost the ability to live independently, relying entirely on hosts. In the grand scheme, this isn't regression, it's specialization. Evolution doesn't care whether you're simpler or more complex, only whether you survive long enough to pass on your genes. The idea that life might devolve still unsettles us because it collides with the myth of progress. We like to imagine a trajectory from chaos to order, from primitive to advanced. But nature is indifferent to our metaphors. If the climate warms, if predators vanish, if resources shift, life rewrites itself. What we perceive as forward or backward are just different directions through the same landscape. Evolution does not honour our sense of hierarchy. It only measures success by endurance. There are even examples of hoaxes, not deliberate human ones like Piltdown, but natural ones, where the evidence seems to lie. Fossils preserved under strange conditions can merge species together, creating chimera-like forms that never actually existed. Rock compression can distort bones beyond recognition. A creature might appear transitional, simply because time has blurred its edges. Evolution's pranks are sometimes geological, not genetic. The fossil record is a fragmentary jigsaw with most of the pieces missing, and occasionally nature misleads us just for fun. To study evolution, then, is to study imperfection. Every discovery is partial, every conclusion temporary. Patterns emerge only when we step back far enough to see repetition in the chaos. And what we find is humbling. Nature reuses designs, revisits past forms, and occasionally rewinds the tape entirely. Evolution's creativity lies not in invention but in adaptation, in finding old answers to new problems. This is why the notion of a missing link collapses under scrutiny. There is no singular connection to be found because there is no singular direction to trace. The web of life doesn't move from less to more, but from different to different again. Every branch, every loop, every convergence adds texture to the story. What looks like a backward step or a dead end is often just another route through the same terrain. And so we learn to laugh with evolution, not at it. It deceives us, confuses us, and occasionally delights us by contradicting everything we thought we knew. Snakes that almost grow legs, whales that remember the ocean, birds that rediscover flight, each of them a reminder that nature plays without rules. It is not progress that defines life, but persistence. In a universe where even extinction can be temporary, perhaps the greatest evolutionary trick of all is that life keeps finding ways to begin again. Could the last common ancestor think about thinking? It's a strange question, but an important one. Somewhere between the mind of a chimpanzee and the mind of a human lies an invisible threshold, one that language, empathy, and curiosity eventually crossed. We can't dig up thought, can't fossilize awareness, yet every twitch of cognition leaves fingerprints in behavior. By tracing what humans and great apes still share, we glimpse what might have lived in the mind of that last ancestor who stared out at a changing world and began, perhaps for the first time, to notice that other minds were staring back. If we strip away the mythology around intelligence, we find that our mental abilities didn't emerge overnight. They grew in layers, like sediment in a long geological record of thought. Tool use, social cooperation, deception, grief. These are not uniquely human inventions, but shared legacies. Modern chimpanzees, bonobos, and orangutans show us a fragment of this inheritance. They use sticks to fish for termites, stones to crack nuts, leaves to collect water. In some populations, these techniques vary from group to group, taught through observation and imitation rather than instinct. That alone hints at something monumental: culture without language. It suggests that the last common ancestor already lived in a world where knowledge could be passed down, not genetically, but socially. Watching a young chimp learn to use a tool is like seeing evolution rehearse memory. It's not instruction as we know it. There are no words, no lectures, no diagrams. There is attention, mimicry, and trial. The student observes the master until movement becomes pattern, and pattern becomes habit. That silent learning may have been the foundation of our own species' intellect. Long before we spoke, we watched. Long before we reasoned, we copied. The mind of the ancestor likely survived not by inventing, but by remembering. From that same root of shared memory grows another branch: empathy. Chimpanzees comfort the distressed, reconcile after fights, and even seem to mourn their dead. They recognize themselves in mirrors, indicating some awareness of self. This is not sentimentality, it's neurology. The circuits that make us wince when we see another in pain are ancient. The last common ancestor almost certainly possessed them. Cooperation too emerges from this empathy. Coordinated hunting, food sharing, and alliance building all require an understanding of others' intentions. Even deception requires a theory of mind, the ability to model what someone else believes so you can manipulate it. When a young ape hides food from a dominant rival, or feigns indifference to protect a secret stash, It's performing an act of cognition once thought to belong only to us. These behaviours form a portrait of a creature neither beast nor philosopher, but something quietly extraordinary, a mind beginning to loop back on itself, to think about what others think, to imagine the unseen. In this recursive awareness lies the seed of imagination and ultimately of morality. The ancestor's brain may have been smaller than ours, but its social complexity demanded intellect. Living in groups means navigating hierarchy, negotiating favours, and predicting behaviour, a kind of social calculus that rewards foresight. For an ape navigating alliances and rivalries, intelligence was not abstract. It was survival. Anthropologists sometimes call this the Machiavellian intelligence hypothesis. The idea is that brains grew not to solve puzzles about the environment, but to solve puzzles about each other. The jungle wasn't the only wilderness, society was. The ancestors' success would have depended less on brute strength and more on reading social cues, remembering debts and recognizing faces. Modern chimpanzees have been shown to remember the faces of dozens of individuals even after years of separation. Such memory suggests a mind attuned to identity, to the persistence of others over time, a subtle kind of narrative thinking. Even play, that most underestimated of behaviours, reveals deep intelligence. Juvenile apes invent games, take turns, simulate conflict, and sometimes even cheat. Play requires trust, imagination, and an understanding of fairness, traits that prefigure our own moral instincts. It's easy to overlook how much philosophy is hidden in a game of tag. To chase, to stop, to reverse roles, to laugh, all depend on grasping that actions can be symbolic, not just literal. The mind of the ancestor may not have written poetry, but it knew metaphor in motion. Communication among these early minds would have been complex long before words appeared. Modern apes use an array of gestures and vocalizations to convey intent. A touch to request grooming, a scream to summon allies, a bow to show submission. Some of these gestures have universal meanings across species, implying they are ancient, older than language itself. The last common ancestor likely lived in a symphony of signals, where emotion, sound, and body language interwove into meaning. A snort could warn, a glance could command, and a posture could forgive. Over time, such signals may have become more structured, paving the neural road that language would later travel. But what about self-awareness? The mirror test, placing a mark on an animal's face to see if it recognizes itself, has long been used to probe this question. Chimpanzees, orangutans, dolphins, and even magpies pass it. That suggests that awareness of the self as an object in the world is not unique to us. The ancestor likely possessed at least a rudimentary version of this capacity. It may have been aware of its own body, its own agency, its own role within the group. Self-awareness is the first step toward introspection, the beginning of consciousness reflecting on itself. Emotion, too, runs deep. Studies of modern great apes show behaviours resembling human grief. Mothers carrying dead infants for days, even weeks. Groups gathering quietly around fallen members. These acts do not prove abstract thought, but they reveal a recognition of a loss, of absence. The ancestors' world was not only physical but emotional. Its cognition was not cold calculation. It was threaded with feeling. The same chemistry that binds us in love and sorrow, oxytocin, dopamine, cortisol, has ancient origins. We inherited not only the capacity to think, but the capacity to feel that thinking matters. Cultural learning in apes adds another layer to the picture. Different populations use tools differently, develop local customs, and pass them down generations. In one region, chimps use sticks to fish for termites. In another, they use leaves as napkins. Such behavioural diversity suggests proto-culture, a web of traditions evolving alongside biology. If culture existed in our shared ancestor, then evolution was not only genetic but mimetic. Ideas competing, adapting, and surviving just like genes. The ancestors' world was already thick with imitation, innovation, and accidental invention. It's tempting to imagine that this cognitive bridge between ape and human was crossed by a single, dramatic leap, a mutation or spark of genius. But what we see instead is continuity. The difference between them and us may be more quantitative than qualitative, a matter of degree, not kind. The human mind didn't appear suddenly. It crystallized gradually through the slow accumulation of small mental skills, each building upon the last. Tool use sharpened coordination. Coordination required memory. Memory invited imagination. Imagination gave birth to stories. What began as practical intelligence became reflective intelligence. Still, there are limits to what we can infer. Fossils can tell us how a skull was shaped, but not what it dreamed. Neural circuits do not fossilize. What we have are clues left in behavior, glimpses from modern relatives, and the structure of our own cognition, which still bears traces of that ancient design. Our minds remain mosaics of the old and the new. Beneath the complexity of human reason lies an architecture shaped by the same pressures that moulded ape societies, the need to cooperate, to deceive, to nurture, to belong. If the ancestor thought about thinking, it was likely not in the abstract way we do, but in practice. It might have paused before acting, reconsidered, or hesitated in uncertainty. It might have sensed intentions behind eyes, or felt guilt after aggression. Those tiny hesitations are the beginnings of reflection, the moment a mind becomes aware of its own processes. In that awareness lies the root of morality and creativity alike, and yet, for all its sophistication, the ancestor's cognition was not aimed at discovery or philosophy. It was aimed at survival, to be aware enough to anticipate danger, to empathize enough to raise offspring, to plan enough to secure food. These were the evolutionary victories of thought. From such utilitarian origins, consciousness expanded accidentally, like a side effect of living in social worlds too intricate to navigate without introspection. In the end, the last common ancestor was not a philosopher or a beast, but something far subtler, a creature whose mind was beginning to bend back upon itself, noticing patterns, storing them, sharing them. A being that lived in both the present and the remembered past, caught between instinct and intention. We may never know what it felt like to inhabit that mind, but in the gestures of a chimp, the curiosity of a child, and the empathy of a stranger, we still echo it. If the ancestor could think about thinking, it was only in the most practical, embodied sense. To understand what others knew, to imagine what might happen next, to weigh cause and consequence. And maybe that was enough. From that small spark of self-awareness, everything else followed. Language, art, morality, science. The vast architecture of human thought began as a single mirror glinting faintly in the forest, reflecting a face that was almost, but not quite, our own. If there was never a missing link, what does that make us now? Perhaps not the final rung on a ladder, but one of many bends in a river still flowing. Every species is a link, temporary and passing, suspended between what came before and what comes after. To call something missing is to assume the story was meant to arrive somewhere, and that arrival was us. But evolution has no destination, only momentum. We are not the end of the chain, we are the current, briefly aware of itself. The idea that we were ever separated from the rest of life is an illusion of comfort. It lets us believe that humanity stands apart from nature, not within it. Yet every breath, every strand of DNA, every neuron firing inside the human brain is ancient. The same molecules that shaped the first bacteria still hum inside our cells. The calcium in our bones once belonged to corals, the iron in our blood to dying stars. We are not a new creation, but a recombination, a continuation of matter trying to persist in a universe that constantly forgets it. Science has been humbling us for centuries. Each discovery pushes the centre of importance further from where we placed it. Once the Earth was the universe's stage, then it became a planet among many. Once humans were divinely separate, now we are primates with complex memories. Yet the more we learn, the more beautiful the continuity becomes. Knowing that we share 99% of our DNA with chimpanzees does not lessen us. It situates us. It reminds us that intelligence, empathy and culture are not miraculous exceptions, but the natural flowering of time and cooperation. The so-called missing link never existed because evolution never lost the thread. The fossil record doesn't show leaps. It shows transitions so gradual they defy tidy storytelling. Between every ancestor and descendant lies not a single form, but thousands. blending imperceptibly. There was no moment when a creature woke up human. There were only generations that became slightly more curious, slightly more social, slightly more aware of their own reflection in the water. The boundary we draw between animal and human is linguistic, not biological. That continuity carries both humility and awe. To realise that our ancestors were not crude or incomplete, but simply adapted to their own worlds, is to see time not as a climb, but as a conversation. Every species that ever lived participated in this dialogue, testing, failing, enduring, passing something along. We are not their outcome, but their echo. The search for the missing link, then, was really the search for ourselves, for a story that made sense of our uniqueness. But uniqueness was never the point. Life is variation, not hierarchy. When we look back across millions of years of fossils and genomes, what we see is not progress, but persistence. Evolution rewards not perfection, but compatibility. It is a system that keeps the game running, not one that crowns winners. The Earth does not keep score. Species rise, diversify, vanish and transform again, like waves forming and dissolving in the same tide. Our presence here is the brief result of that endless motion. No more inevitable than a gust of wind, but no less meaningful for its brevity. And that is perhaps the most profound realization science has given us. Meaning does not require intention. The fact that life can emerge, self-organize, think and look back at itself without a plan is astonishing enough. Evolution's beauty lies in its indifference. From that indifference we create compassion. From randomness we extract pattern. From deep time we make memory. The missing link was never about a fossil. It was about our need for coherence in a universe that has none to give. But science itself is also evolving. The models we build, the ladders, trees and braided streams, are not truths but metaphors, scaffolds that let us glimpse the shape of something too vast for certainty. Each generation refines them, not to reach an endpoint, but to better capture complexity. Knowledge, like evolution, is iterative. What we know today will one day seem primitive, yet necessary. Every theory, every diagram, every fossil is a step in our species' attempt to see its own reflection more clearly, and perhaps that's what sets us apart, if anything does. Not that we think, but that we know we are thinking. We are the lineage that studies its own origins, the only animals who turn curiosity inward. That curiosity is not arrogance, it is survival at another scale. The same impulse that drove the first primate to shape a stone drives the scientist to sequence DNA. Both are acts of continuity, of using knowledge to extend life. We are still doing what the last common ancestor did, testing, learning, adapting, and in our own way, grooming each other through information. It's strange to realize that the thing we once called the missing link might be us, not because we complete the chain, but because we're still part of it. Our species, Homo sapiens, is not the culmination of evolution, but one of its latest experiments. One day, we too will become fossils in the continuum, perhaps misunderstood by descendants who see us as primitive. The difference is that we know it. We live with the awareness of impermanence and the ability to record it. That awareness is both a gift and a burden. It gives rise to science, art and philosophy, but also to fear, to the knowledge that we too will vanish. Yet perhaps the true legacy of evolution is not in the survival of species, but in the continuity of curiosity. Every creature that learned, that adjusted, that left a trace contributed to this slow awakening. From that perspective, extinction is not failure, it is transformation. Life is never missing, it only changes form. We often speak of deep time as though it were a distant, unreachable dimension. But it is here, folded into every cell of our bodies. When we inhale, we share molecules with trilobites. When we dream, our neural architecture whispers in patterns inherited from ancestors who had never seen fire. The past is not gone. It is metabolized. We are built of memory, even when we don't remember. Perhaps that's the quiet miracle hidden behind the myth of the missing link. The realization that there was never a line to cross, only a path to follow. Every discovery in anthropology, every genome sequenced, every fossil brushed free from stone doesn't reveal where we began. It reveals that we never truly began. Life didn't start over with us. It continued through us. We are not separate from the history of the world. We are its latest sentence, and maybe that is why the story of evolution still moves us, even in its messiness. It speaks to something beyond intellect, a desire to belong in the grand pattern, to know that our existence, however brief, participates in something ancient and ongoing. The missing link was never missing because the connection was never broken. We are bound to the earth and to everything that has lived upon it. The more we uncover, the less certain we become, and that is how knowledge should feel. Science does not replace mystery. It refines it. Every fossil raises new questions. Every discovery humbles us further. To understand that there is no final answer is not despair. It is liberation. It means the search never ends, that curiosity itself is the inheritance of life. So, if there was never a missing link, what does that make us now? Perhaps nothing more than witnesses, briefly conscious, briefly curious, passing along the light of awareness before it fades again into the long night of time. But even that, in the scale of the cosmos, is extraordinary. For a moment, matter knew it existed. For a moment, it wondered why. Thank you, fellow Sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the Sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.